My name's Mark Rivers. I work for the University of Chicago, but I am basically always at the Advanced Photon Source at Argonne National Lab. Today I'm speaking to you from my office at the APS. Normally, when we're doing beamline experiments, as we will be today, I would actually be sitting out at the beamline. But because of COVID, I would have to be wearing a mask out there, and also it's kind of noisy. So what I'm going to be doing is sitting in my office, but running the screens with VNC session for the Beamline computers. So you'll be seeing exactly what you would be seeing if you were sitting at our Beamline. Let me share my screen here. Okay, so as I said, I'm Mark Rivers. I'd also like to thank Yanbin, Tim Officer, Manshu, and Charlie from GSECARS who are helping with the technical parts of this presentation, and also Doug Schmitt, who I think I'll be joining us to talk a little bit about the samples that we'll be measuring today. Doug's from Purdue. So I've changed the schedule just a little bit based upon how the session went yesterday, where this introductory talk took about an hour and 15 minutes instead of just an hour. But so the schedule's rearranged by 15 minutes here and there. And there's no guarantee we'll stick to this exactly today, but this is roughly what we plan to do. So I'm going to start out with this introduction to synchrotron computed microtomography. And then we'll take a break, 10-minute break or so. And then we'll actually go out to the beamline. I'll go out to the beamline. I'll speak to you there using BlueJeans on my phone. And you should be able to show you the inside of the hutch and how we actually mount the samples and start the data collection. And then I'll come back to my office. Doug will give a little talk about the samples that we're measuring. And then we'll actually collect the data on those samples. We'll then take another break and then actually go through the reconstruction process with an overview talk, and we'll really reconstruct the data we collected earlier. So in this introductory talk, I want to give you a brief introduction to synchrotron radiation sources for people who are not expert in that. Talk about the advantages of synchrotrons for imaging and tomography, describe our beamline and the types of computed tomography we do at our beamlines, the apparatus that we'll be using for the specific measurements this afternoon, how we collect the data, and then, as I said, we'll end with actual data collection on some real samples. So I'm here at the APS, which is a 7 GeV high brightness electron storage ring. You can see it here. It's about 1.1 kilometers in circumference, the storage ring is. Around the storage ring, tangential to the accelerator, are the X-ray beamlines. And there are roughly 70 X-ray beamlines at the APS that can be running all at the same time and doing a wide variety of science, from protein crystallography for COVID to X-ray scattering of various sorts, X-ray imaging, X-ray spectroscopy. And 3 of the sets of beamlines at the APS are actually run by the University of Chicago, not by the APS itself. And I'm at one of those. It's called Geosoil EnviroCars, or GSECARS. It's Sector 13 at the APS. So what are the important properties of synchrotron radiation? First of all, it's tunable over a very wide wavelength or energy range. And synchrotron radiation is used in the infrared There are no infrared beamlines at the APS, but there are infrared beamlines, for example, at the NSLS2 at Brookhaven. And then it's used for soft X-ray and VUV science. That's not the specialty of the APS, but it is the specialty of the Advanced Light Source in Berkeley, for example. And then hard X-rays, which is where the APS really is the specialty. Synchrotron radiation is very bright. That means it's highly collimated, and it comes from a small source. That small source is the electron beam that's circulating in the accelerator. So the radiation has very high intensity. Even if you don't focus it and just use a set of slits in front of your sample, you can put lots of photons into a small spot. Because the source is small, you can focus it very well with X-ray optics and produce beams that are micron or submicron with lots of photons in them. The synchrotron radiation is polarized, which is important for certain experiments, and it can be linearly or circularly polarized and tunable polarization. Synchrotron radiation is pulsed. It comes from bunches of electrons that are circulating in the storage ring. Those bunches are quite short, and particularly compared to the time between them. And at the APS, the time structure is such that in a normal mode, there are 24 bunches filled in the ring, evenly spaced around that 1.1 kilometers, which means the time between the X-ray pulses is roughly 170 nanoseconds, but the pulses themselves are only 100 picoseconds long or something. So there are some experiments that take advantage of that time structure. The experiments that we'll be doing today do not. They just treat the synchrotron radiation as if it were a DC source. But in fact, there are bunches going by, and we're actually measuring radiation from bunches that are happening at about 5 or 6 megahertz. Synchrotron radiation is partially coherent, and which has important applications in some experiments, including the phase contrast imaging that I'll show you today. So how is synchrotron radiation produced? It's produced from relativistic electrons that are going very close to the speed of light. And the figure of, or the parameter that tells you just how relativistic they are is called gamma, which is defined as the ratio of the mass of the relativistic electron to its rest mass. And in practical units, gamma is equal to approximately 2,000 times the energy of the machine or of the electron in GeV, or billion electron volts. Gamma is important because for synchrotron radiation, 1 over gamma is approximately equal to the full width half max opening angle of the synchrotron radiation at some characteristic critical energy. And the critical energy is defined by this equation here, which says that it's 0.665 times the square of the energy. So you see the critical energy goes up as the square of the machine energy times the magnetic field in Tesla. So there, for 3 accelerators, or light sources, I should say, in the US, the advanced light source runs at 1.9 GeV. NSLS2 at Brookhaven runs at 3.0 GeV, and the APS currently runs at 7.0 GeV. And these are the values of gamma for those machines, and these are the values of 1 over gamma. So at the APS, 1 over gamma is 73 microradians. So that means that a meter away from the source, the beam would be 73 microns tall, and 100 meters from the source, the beam would be 7.3 millimeters tall. Where we're working today is roughly 56 meters from the source. So it's something like 4 millimeters. Yeah, it's 4.4 millimeters is 1 over gamma. And the critical energy of an APS bending magnet is about 20 keV. That's the half power point. That means half the power of the X-rays coming out of the APS are below 20 keV, and half are above. And it's also approximately the energy where the maximum flux occurs. So there are two types of sources of synchrotron radiation. The first are bending magnets or dipole magnets. These are the magnets that keep the electron beam orbiting in its more or less circular orbit around the machine. Actually, the APS, it's not a circle, it's a 40-sided polygon with rounded corners. And those rounded corners are the bending magnets, and then there are straight sections into which are inserted these periodic magnetic field devices called insertion devices. And there are two types. One is a wiggler, which has a high magnetic field and or a large period. So the electron beam has a large deviation from its orbit, greater than 1 over gamma in terms of its angular deviation. An undulator, on the other hand, has a medium magnetic field and a small period, and the electron beam deviation is less than or about 1 over gamma. Actually, at the APS right now, there are no wigglers, there are only undulators. So how are X-rays produced? We've got a cartoon here, so we've got this beam of relativistic electrons. If they go to a bending magnet, they are bent as they go around this corner here, and as each point, as they're being accelerated around this corner, they're emitting radiation with an opening angle of 1 over gamma. But because they're sweeping around the corner like the headlight on a train as it goes around a corner, it sweeps out a relatively large angle horizontally, but the vertical opening angle is 1 over gamma. And this cartoon is intended to show that this is a polychromatic beam of X-rays. It doesn't mean it's dispersed in the horizontal here. Each point along this fan of radiation has the same X-ray spectrum. The insertion devices schematically look like this. They're periodic magnets in the straight sections, and the electron beam undergoes an oscillatory motion horizontally as it goes through this periodic magnetic array. As it does, if it's an undulator, the radiation from one pole interferes constructively or destructively with the radiation from the next pole, and that results in a beam that is highly collimated in both the horizontal and vertical directions, much more collimated than 1 over gamma. So these beams are like a millimeter tall and a millimeter wide in the experimental stations, if there is, with no focusing optics. And this just shows the bending magnet as this searching sweep light with a 1 over gamma in the vertical and a broader fan in the horizontal. A wiggler, which is kind of like a whole bunch of bending magnets in a row, interfering incoherent, with no interference, it's incoherent. So it has a broad fan. And then the undulator with this much narrower fan. In the spectral domain, so this is now photon energy against the log of the brightness, you see the bending magnet is down here, the wiggler with a very smooth spectrum. The wiggler is up here. If it were the same magnetic field as the bending magnet, but just 30 poles, it would be just the bending magnet 30 times higher. And then finally, you have the undulator, which has this very spiky spectrum. So at certain energies, there's constructive interference, and you gain, 2 orders of magnitude over the wiggler, or 3 orders of magnitude over the bending magnet. And then in between those peaks, there are almost no photons. These peaks can be adjusted by opening and closing the gap on the undulator that changes the magnetic field. I'm sorry about that stripe on my face. That just happens to be where the sun is coming through the shade right now. At the APS sectors all have, they all have an undulator, and many of them also have a bending magnet. And if we look, at over a very large range of logs in brightness here, you start with X-ray versus the year. So with X-rays being discovered just over a century ago, the intensity with the brightness was down here like 10 to the 7th, and then rotating anodes, maybe a factor of 10 higher, bending magnets, wigglers, undulators, and then finally free electron lasers up here. So you see there are more than 10 orders of magnitude in brightness between these lab sources and undulators. This is what the inside of the advanced photon source looks like. It's basically 1.1 kilometers of close-packed magnets. This red magnet here and here, these are the bending magnets, the dipole magnets that produce the bending magnet radiation that we're going to be using for the experiments today. We're going to be running on a bending magnet. These blue magnets are focusing magnets that keep the electron beam tightly focused and small. And then this is one of those undulators with the periodic magnetic array here. You see it's sort of a massive structure. That's because we need to open and close the gap on this with micron precision, but there are enormous magnetic forces operating between these pole pieces, so we need a very strong structure to be able to do that. This is a plot showing the intensity, which is just the photons per solid angle per unit bandwidth, independent of the size of the source, for a bunch of sources. The APS ones, let's pay attention to those. They're the black ones. So this solid black line here is the APS bending magnet, and this solid black line here, APS U33, is a typical APS undulator. Now this doesn't show the spiky spectrum. This is the tuning curve. So sort of the maximum intensity or bright intensity you could get out of this undulator as you change its gap. The dashed black lines here are after the APS upgrade, which is happening in a couple of years. The bending magnet doesn't change much. It's a little more intense at low energy and about a factor of 2 less intense at very high energy. But the undulators get significantly more intense, but not as much as they go up in brightness. So this is now brightness, which takes into account the size of the source. This APS upgrade is mainly decreasing the size of the electron beam in the storage ring at the APS, in particular in the horizontal direction. So you see the bending magnet brightness goes up by about a factor of 30, I think, and the undulator brightness goes up by a factor of 100 or so. So we're getting a much brighter source with the upgrade. This just shows an APS bending magnet today. This is the number of photons per second per solid angle as a function of energy. So you see it's dropping fairly significantly between 20 and 100 keV. This is the size of the beam in our experimental station. So at 20 keV, the full width half max is about 6.5 millimeters. At 100 keV, it's 2.6 millimeters. So the beam gets significantly narrower in the vertical direction as you go up in energy. We have a mirror in this beamline with which we can either defocus or defocus this bending magnet beam. And as you'll see today, with the defocusing, we can make the beam bigger than 5 millimeters, even at 100 keV. And with the APS upgrade, the beam gets a little bit bigger intrinsically because the storage ring energy is going to go from 7 to 6 GeV, but it's about the same. So why do we want to use synchrotrons for X-ray imaging? Well, as I said, the source is bright, so we get a lot of flux in the beam for doing things like full field imaging. Because it's bright with a small source, we can focus it to a very small spot for doing imaging like fluorescence or diffraction or projection imaging. The X-ray spectrum is continuous. That means if we put a monochromator in the beam that selects a particular energy, we can go to an energy that's optimized for a specific sample thickness and composition, or for exciting a specific element in the periodic table. Or we can scan the energy for experiments like X-ray absorption fine structure. If we don't use a monochromator, we can get very high flux for high-speed imaging, or we can get efficient excitation of a large number of elements for X-ray fluorescence. The source is partially coherent, as I mentioned, and that's useful for phase contrast imaging. For synchrotron tomography, we've got a parallel beam geometry that avoids some of the artifacts you get in cone beam geometry, which is what laboratory CT machines use. And finally, at the APS, we've got an abundant source of quite high energy X-rays that can be used to study, thick samples or high atomic number samples. But I should say the energy generally is not as high as a high energy X-ray tube that would be used in industrial scanning CT, like for examining welds in a steel pipe or something like that. So this is the layout of our sector at the APS, Sector 13 at GSECARS. As I mentioned, we've got two beam lines, an undulator beam line and a bending magnet beam line. So this up here is the undulator beam line, and there are three experimental stations here, the IDE, IDC, and IDD. IDE is a dedicated X-ray microprobe for doing X-ray fluorescence, X-ray microspectroscopy, and microdiffraction. IDC has a large diffractometer that's used for surface scattering studies. It's also used where we can put a Paris-Edinburgh large volume press. And then in the IDD station, we have a double-sided laser heating for the diamond anvil cell diffraction and spectroscopy, and a 1,000-ton multi-anvil press for high-pressure, large-volume experiments. On the bending magnet, we have two experimental stations. We have a side station here that's called 13BMC. That has another large diffractometer. That's used for, again, for surface scattering, but it's also used now a lot for single crystal X-ray diffraction in a diamond anvil cell. And then the end station, 13BMD, has three experiments. It has a diamond anvil cell Brillouin scattering experiment. It has microtomography, and it has a smaller multi-anvil press, a 250-ton press. So I actually just went through these. This is in the X-ray microprobe, the techniques that we've got, the IDC, diffractometer, and then in BMD, we've got these, the multi-anvil press where we can do imaging, we can do diffraction. We've got the tomography we're going to talk about in detail today, Brillouin spectroscopy, yeah. So in the 13BMD station, which is where we're going to be running today, that end station on the bending magnet, there are three different modes we can run in there. The first is white beam. White beams means we have no X-ray optics except slits and absorbers. We're basically taking the beam directly from the storage ring. We can have monochromatic beam, where we have a high resolution silicon 111 double crystal monochromator. That has a very narrow energy bandwidth, a few times 10 to the minus 4. So that means we're throwing away 99.99% of the X-rays that come out of the source, but we can now have a very small energy bandwidth that's important for certain experiments. And finally, the mode we're going to be running today actually is called pink beam. Pink beam is white beam that's been reflected from an X-ray mirror. It's called pink beam by analogy with visible light because it's lost its high energy photons, which in the visible would be blue. So you're left with the reddish light, or it's called pink light. Mirror optics are achromatic, so all energies are reflected at the same angle, and if you're focusing, they all end up at the same place. Unlike, for example, focusing with diffractive optics or zone plates. So we can focus either the pink beam or the monochromatic beam. The mirror that we have can be used for focusing, and it is for the diamond anvil cell experiments in that station. We can focus the beam down to under 20 microns in the vertical direction. And we have a second mirror that focuses horizontally. But it can also be bent the other way to defocus the beam, and that's actually what we'll be doing today. And of course, focusing with mirrors can greatly increase the flux on the sample. So the way X-ray mirrors work is that if an X-ray beam is incident on a flat surface below a certain angle called the critical angle, it will be totally externally reflected. And those critical angles are small. They're a function of the atomic number, really the electron density in the mirror surface, and they're a function of energy. The critical angle is a function of energy. So for example, at 10 keV, the critical angle for gold is 9 milliradians, which is about a half a degree. For nickel, it's 6 milliradians, so about a third of a degree. And for silicon, 3 milliradians, or about a sixth of a degree. And this shows the reflectivity of a mirror as a function of energy at a fixed angle of 3 milliradians. So you see silicon reflects very well up to about 10 keV, and then it just plummets. Nickel up to about 20 keV, and platinum up to about 30 keV. The mirror that we're going to be using today is platinum coated, but we're going to be using it at 1.5 milliradians instead of 3 milliradians. So it's reflecting, actually, this cutoff is at about 60 keV rather than 30 keV. This is how focusing with a mirror works. If you remember from high school geometry, an ellipse is the figure that focuses a point to a point. An ellipse has two foci, a source, and here we call it a source point and a focal point. The source point is the electron beam in the storage ring. The X-rays are coming down and they're hitting this mirror. The mirror is not the full ellipse, of course, and the X-rays aren't emitted in all directions. They're only emitted in this small forward direction. So we have a piece of this ellipse, our mirror here, that is, the mirror was manufactured flat, but we're bending it to the shape of this ellipse here. And that will then focus the beam at the sample here, and it will demagnify the source by the ratio of F1 to F2. And in our case, this is about, I think, 45 meters and about 7 meters. So it's demagnifying the source by roughly 6 to 1, something like that. But we can also bend this mirror the wrong way. So instead of bending it to a concave shape, as shown here, we can bend it to a convex shape, and it will blow the beam up and make the beam at the focal point bigger than it would have otherwise been, if, say, compared to a flat mirror. So this is a schematic and a photographs of what it actually looks like. This mirror's about 1.2 meters long. The beam is coming from below and reflecting off and bouncing down, so the mirror bounces down. And in the ultra-high vacuum chamber, there's a bender with a 2-point bender, so we can apply a moment on each end of the mirror to bend it into the ideal elliptical shape. So when we run in pink beam on 13 BMD, we've got some water-cooled slits, both upstream of the mirror and just before the sample. We've got some aluminum and copper absorption filters upstream that we can put in the beam to get rid of low-energy photons. And then we've got this mirror. So the mirror's at 49.5 meters from the source. It's got about 1 meter of optical aperture. It bounces the beam down. As I said, it's platinum coated. We can adjust the pitch. So, as I said, we're at 1.5 milliradians today, but we could change that to change the critical energy that it bounces off the mirror. And we can change the curvature, as I said, to either focus or defocus. So this is what a spectrum from the mirror looks like. So the black line here is the spectrum from the APS bending magnet itself before it sees any optics in the beam line. So you see the peak is just below 20 keV. And, I forgot to mention at the beginning, I'm sorry, that, I'd like to keep this interactive. So if you have questions, you can raise your hand, and Yanbin is keeping an eye on that, and he'll let me know if somebody has raised their hand with a question. Or you could just unmute your microphone and ask the question if we're not spotting that you've got your hand raised.
Or you can type it in the chat.
Yeah, if you have a question and you don't want to say it, you're welcome to just type it in the chat. Okay, so here is the black is the raw spectrum out of the bending magnet. You see it's falling off. This is a linear scale now, not a log scale. So it's falling off at 100 keV. It's falling off pretty steeply with energy, actually on both sides, in the low and high energy side. The blue line here is what happens when we put a 1 millimeter aluminum absorber in the beam. So you see, if it does very little at high energy, of course, because the beam just goes right through the aluminum, but it's effectively getting rid of almost all the photons below 15 keV and maybe half of them at 20 keV. And then the red line here is what happens if we have both the aluminum absorber and the mirror at 3 milliradians. So you see, we've now made a broad bandwidth beam here, but we've gotten rid of a lot of the high energy photons and the low energy photons. And the green line here is the energy, just for comparison, of the iodine K absorption edge, which is at about 33 keV. And if we were using the monochromatic beam mode, that would be taking at 33 keV, for example, that would be taking a very, very thin slice, thinner than the width of this line, out of the spectrum. And so, the intensity would be this, but only at a very narrow energy bandwidth there. This is a blow up of the layout of that bending magnet beam line. So we've got a set of those water-cooled filters here at 23 meters. We put them far upstream, so any scatter from the filter is, been long gone by the time we get into the experimental hutch down here. Then we've got a set of water-cooled slits at about 23.8 meters. The monochromator, which is used when we run the beamline in monochromatic mode, but today that's been moved out of the way, so we're not using the monochromator. We've got another set of vertical slits here just before the mirror. So this is where that water-cooled silicon mirror is at 49.5 meters. Then we have a final set of slits in the hutch just upstream of the optical table where we'll be doing the tomography. And then this is where we'll be doing the tomography today on this table. And then at the back end of the hutch is where the 250-ton multi-anvil press is located. So schematically, this is what the absorption tomography setup looks like. We've got either parallel beam of monochromatic or pink beam coming from this APS bending magnet source. We can make a beam that's anywhere from 1 to 50 millimeters in width and up to about 6 millimeters vertically. And we can go from 1 to 20 micron resolution depending on the field of view. We've got the beam comes down here, hits the sample that's on top of a rotation stage. The transmitted X-rays basically cast a shadow on the scintillator, which is a single crystal lutetium aluminum garnet that converts those X-rays into visible light. That visible light is now imaged with a lens of some sort. It could either be a microscope objective, or today we're using a Nikon macro lens. Images the scintillator light onto a camera. We're using today a CMOS camera that's quite fast, 1920 by 1200 pixels. And the experiment is basically to rotate the sample 180 degrees and acquire images every 0.2 degrees, or today we'll be using every 0.1 degree. And the data collection time, if we're in monochromatic mode, to collect a full 3D volume here, is anywhere between 10 and 30 minutes, because the exposure times are a second or several seconds per projection, per angle. But in the pink beam mode that we'll be using today, the data collection times are anywhere between 10 to 100 seconds. And then it takes 2 to 5 minutes to do the reconstruction of the data. So this is a detail of what the apparatus in 13BMD looks like. It's the first thing is the sample here. That's number 1. The X-rays are coming in from the right. The sample is mounted here on top of a set of translation stages, number 2 here. So we've got XY translation stages. Those are used to center the beam on the rotation axis. So just below those translation stages is a rotation stage. That's used to rotate the sample and collect the projection images. The rotation stage sits on top of a vertical translation stage that's got 30 millimeters of travel. So we can scan the height of this sample by 30 millimeters. And then under that is a horizontal translation stage that's moving in and out of the picture here. And that's used to move the sample and the entire apparatus out of the beam when we want to collect what are called flat field images, or images with no sample. The entire thing sits on a number 6 down here, which is an optical table with 5 motorized degrees of freedom. So it's got X and Y, which means vertical and horizontal in and out of the beam. It does not have a translation along the beam direction. We don't really need that. And then it's got 3 rotational roll, pitch, and yaw adjustments. The beam, after it goes through the sample, here's the scintillator. And then there's a 45-degree mirror here, which bounces that light up to this lens. In this case, this is the lens we'll be using today. It's a Nikon macro lens that's designed to do 1-to-1 imaging if there's no extension tube, or we can put in an extension tube to get a smaller field of view, or we can defocus this, which adjusts the working distance, and so we can get a bigger field of view. So with this lens, we typically go from fields of view of about 6 millimeters to 20 millimeters. We use microscope objectives to get to higher fields of view, smaller fields of view. Number 9 here, this is the camera. You can't really see it because I've got it wrapped in lead to protect it from the X-ray beam. When we're using pink beam, there's a lot of radiation in the hutch, and electronics can get damaged, so we wrap sensitive electronics in lead. Number 10 here is a 4-degree of freedom stage on which the camera and the lens are mounted. The most important adjustment there is the vertical height, because that adjusts the focus of the lens, and the lens is focused on the scintillator here. So when we change samples, we don't need to refocus because we're not focused on the sample, we're focused on the scintillator. And then finally, number 12 here is not involved in the tomography experiment. Those are optics that are used for the Brillouin spectroscopy when we run diamond cell experiments in this station. I should say that this stage we've been using for many years, but it does have some limitations. So we plan in the very near future, hopefully by the next APS run in early 2021, to replace this stage for tomography with this new stage here. So the existing stage only has a capacity of about 3 kilograms. I mean, sometimes we push that, but it can't hold very heavy loads. It also has a maximum distance from the pink beam up here where the sample is to this surface of this sample stage here of about 75 millimeters. So we can't put in a very tall assembly here, like say a pressure vessel, for which that distance would be more than 75 millimeters or so. So we can't use a large in situ apparatus. Also, this rotation stage here is a ball bearing stage, which has limited accuracy. It's got 1 or 2 micron run out and angle wobble. So this is a new stage we've just gotten. It's got a hexapod below it, which has a very high weight bearing capacity, and lots of degrees of freedom, 6 degrees of freedom. And on top of that, we're mounting this, which is an air-bearing rotation stage, which has got about 250 nanometers of runout and much lower wobble, and has a much higher load-bearing capacity. Unfortunately, to get this running, we need to make a hole in this table because this would be too tall. So this is going to be mounted on a plate below and stick up through that optical table. The optics will be mounted on that optical table as they are now. So as I said, this should be available for the next run. Okay, I'm going to change gears here and talk a little bit about how X-ray tomography works. I think you're all familiar with Beer's law that says, as a beam goes through an attenuating material, like an X-ray beam going through a sample, the transmitted intensity divided by the incident intensity is equal to e to the minus mu x, where mu is a linear X-ray attenuation coefficient and x is the thickness. So the beam decays exponentially with distance. And what we measure, if we put our scintillator and camera back here, is we're measuring the line integral of the absorption along that path through the sample. And if we imagine that this is broken up into voxels, and so we've got a distance increment ds, where there is a single linear attenuation coefficient, mu sub s, or mu of s. What we would like to know to do tomography is, what are these individual mu's when all we've measured is the line integral, or the sum of all those mu's. And it turns out that the solution to that problem is not obvious, but if you measure the line integrals through, say, this voxel, not just over one angle here, but through many angles, and where, of course, you're then measuring line integrals that involve different pixels for each angle that you measure as you rotate the sample here. There is sufficient information there to reconstruct what the individual mu's in each pixel must be. As I said, that's not obvious. The Nobel Prize in the 60s was awarded for the discovery and implementation of that. I think mathematicians had probably known it before that, but actually making a practical instrument was done then. And as you know, I mean, it just revolutionized medicine, because you could now make not just radiographs of patients, but three-dimensional cross sections through patients. And there are different types of computed microtomography, geometries. The simplest, and called first generation, just uses a pencil beam. So you have some slits or some focusing that makes a very small beam that passes through your sample, and a single detector here that doesn't have any position information, just for instance, like a scintillation X-ray counter. And then what you have to do is scan the beam, scan the sample through the beam, and collect NX intensities at each of those NX positions. Then you rotate a little bit, you translate again, you rotate, you translate, and in the end, you've ended up with n rotations times n translations, measurements of the intensity. And that gives you enough information to reconstruct a single slice through the sample. Obviously, that's slow because it involves n squared motion position measurements. The next would be a fan beam. If you have a one-dimensional detector here, a strip detector, you could make a beam of that's as wide as your detector, but just a small height. Then all you have to do is rotate your sample, so it's just n rotations, and you've got one slice. The next step is to go to third generation. If you do that at a synchrotron, you've got effectively a parallel beam. So you've got a beam here that when it hits the sample is the same size as when it hits the detector, because this distance is very small compared to the distance to the source. So it's effectively a parallel beam. And now this requires a two-dimensional detector. From a historical note, I started doing computed tomography at the synchrotron at Brookhaven in 1987. We published our first paper. That was first generation CT. And it took about an hour to collect one slice, and it took about an hour to reconstruct one slice on the computers that were available at the time. As you see today, we're going to collect 1,200 slices in about 20 seconds, and we can reconstruct them all in about 40 seconds. So things have come a long way. There's also third generation for a laboratory source that would be called cone beam, because the distance from the source to the sample and the detector is small. So you have a divergent beam, not a parallel beam that goes through the sample. You do have an advantage here, because if you move this sample close to the source, it magnifies onto the detector. You move it close to the detector, and you're doing more like one-to-one imaging. So you've got a variable magnification here, which we don't have with the X-ray beam in the synchrotron. We have to do our magnification at the optical after we've converted the X-rays to light. So what are some of the requirements for tomography? The first one basically comes from sampling theory that says that the number of projections, NP here, should be greater than or equal to pi over 2 times the number of pixels in the horizontal direction in our case. In other words, perpendicular to the rotation axis. So the detector we're going to be using today has 1,920 pixels horizontally. So the number of projections should ideally be at least 3,016. This comes from mathematical sampling theory, but there's actually a simple way to derive this, which is if you imagine that you have a sample that's just the width of your detector, and you have a point on that sample that's, say, upstream towards the source. If you rotate by delta theta such that that point on the sample moves by 1 pixel on the detector, that will result in this criterion, that you need pi over 2 times nx angle steps to have it equal that delta theta in 180 degrees. However, in practice, good reconstructions can be obtained with fewer projections, and often we do use fewer to save time. However, increasing the number of projections also improves the signal quality beyond just this sampling theorem, simply because it improves the signal to noise. You know, you've measured more X-rays, so your shot noise or your statistical noise goes down the more measurements you take. But again, it's a trade-off of what's the quality I need in my image versus how long I'm willing to spend collecting the data, because maybe I need to look at a lot of images, a lot of samples, and I only have 2 days of beam time. The next requirement is, there are a couple of requirements that are basically from completeness. So you should have a uniform material outside of the object at all angles. Usually with the synchrotron, that might be air, but it doesn't have to be air. If your sample was embedded in a cylinder of epoxy, then that's a nice uniform material that is independent of the angle of which the sample is viewed. so that the interesting part of the sample should remain completely in the field of view. However, you can do what's called local tomography, where this is not true. So you can have a sample that's bigger than the field of view, bigger than your detector, and essentially just image at higher magnification some part inside the sample. If you do that, the measured linear attenuation coefficient that you get, the absolute value of that will not be right. And you can have, artifacts depending on just how inhomogeneous your sample is in the parts of it that are outside the field of view. But if all you're trying to see is features in the sample, like cracks, grain boundaries, this can be fine. But if you're trying to get the absolute linear attenuation coefficient, then you need to obey this, object inside the field of view. You have to collect at least 180 degrees of data. Sometimes that's not possible. For example, if you're trying to do tomography in a diamond cell, or you have other sample constraints, that there's some post that gets into the beam, or you have a very planar sample such that you can't get the beam through it at very small angles. But if you have fewer than 180 degrees coverage, that does lead to artifacts. There are some iterative reconstruction techniques that can minimize these artifacts using some a priori knowledge, or using some penalty function that says, I'm trying to basically fill in the blanks with reasonable guesses as to what that missing data would have looked like. A couple of other requirements: the rotation axis must be perpendicular to the beam direction, and that's a mechanical alignment, and it can't be fixed in post-processing. If your beam is not parallel to the sample, the rotation axis is not perpendicular to the beam, then as you rotate the sample, you are mixing up information from multiple slices, and there's no way to reconstruct it. The rotation axis should also be parallel to the columns of the camera, and that's needed to do the reconstruction. That's also a mechanical alignment, but that can actually be fixed in post-processing by simply rotating each image such that the rotation axis projection is parallel to the columns of the CCD, of the camera. Sample shape. Samples should be roughly equant in the horizontal plane, and I'm assuming there that the rotation axis is vertical, but I mean in the plane perpendicular to the rotation axis. The vertical size of your sample doesn't matter. So, we can measure some long, skinny cylinder, or a long cylinder, but thin plates are bad, because in one orientation, they're very thin and transparent, and at another orientation, or 90 degrees to that, they're going to be very thick and absorbing. Okay, so question is, how big can my sample be, and or what energy X-rays do I need? So this shows you the 1/E absorption depth for some common minerals, quartz, silicon dioxide, calcium, calcite, calcium carbonate, an iron oxide, and a copper sulfide. And this is as a function of energy, and this is the 1/E absorption depth in microns. And 1/E is like 40% transmission, 60% absorption, and that's sort of about the sample size you want to have, or maybe twice that. And so what you see is that if you're using an X-ray energy of 20 keV, then the 1/E absorption depth for quartz is about 1 millimeter. For calcite, it's maybe 500, 400 microns. For magnetite, it's 80 microns, and for calcite, it's 50 microns. But whereas if you go to 50 keV for quartz, it's 1 centimeter, and for calcite, it's still under 1 millimeter. So you have to know the composition of your sample to figure out, how big can it be at the energies we can work at to be able to get the beam through it. So, twice the 1/E depth is about the optimum size. Absorption varies linearly with the density of the sample, strongly nonlinearly with atomic number, like Z cubed, and strongly nonlinear with X-ray energy, something like E cubed. So at 30 keV, 1/E is about 5 millimeters for quartz, but only 200 microns for calcite. If you're considering, for instance, fluorescence tomography, and you're trying to measure copper inside a quartz, if you add copper in a fluid inclusion in quartz, the 1/E depth for copper K alpha X-rays, which you'd be measuring, is only about 100 microns for quartz. So you're not going to be able to see a fluid inclusion with copper in it that's more than a couple hundred microns below the surface of the quartz crystal. You got to remember that this is the maximum absorption along any ray, not the average absorption. So if you had two chalcocite crystals that are in the same slice of your sample, at some angle they will line up. And at that angle, the absorption may be too large, and essentially you absorb 100% of the beam. And then you don't get a good reconstruction, you get streak artifacts. So this shows something about how we can use the contrast agents to do certain kinds of tomography. So this is a plot of the 1/E absorption depth for water, which is in blue here, for quartz, which is in black, and and for water containing 1 mole% potassium iodide, or in green, or 1 mole% cesium chloride in red. And what you see is that for water with 1 mole% potassium iodide, this green line, the absorption is, of course, greater than pure water, but less than quartz until we get to the iodine K absorption edge at 33 keV. And all of a sudden, at that absorption edge, iodine starts to strongly absorb, and the solution is now more strongly absorbing than quartz. Similarly, for the cesium solution at the cesium K edge, which is at about 36 keV, it's less absorbing than quartz, just below the edge, and more absorbing than quartz just above the edge. So if we measure tomography just below this edge and just above the edge, and we subtract those two images, we can see where is the iodine in the sample. So here's an example of that. So this is a sample of glass beads that's actually got two fluids in it. It's got an aqueous phase that contains cesium and an organic phase, oil, that contains iodine. This is an image below both of those absorption edges. So you see the glass beads are bright, they are absorbing, and the fluid, both fluids are in this pore somewhere. We can't really tell them apart, but they're less absorbing than the glass beads. Now we've gone to 33.2 keV, so we're above the iodine absorption edge, but we're still below the cesium absorption edge. So now everywhere that the iodine is located, in other words, the oil, has suddenly gotten more absorbing. So if we subtract this image from this image, we get this image, and it shows us where the oil is in this sample. If we now go above the cesium edge to 36 keV, we get this image. So now all of the fluid is quite absorbing. And if we subtract this image from this image, we now get an image of where the cesium is, which is the aqueous phase in this case. So this is a very good way to image, two fluids, immiscible fluids like organic and aqueous, in a sample where if you tried to distinguish the oil from the water just on the basis of their absorption without a dopant, you wouldn't be able to do it. Their absorptions are too similar at the energy we have to work at to get through the glass beads. Okay, I'm going to talk a little bit about the pink beam setup here. So we've got aluminum, we've got these slits, we've got the filters, we've got the mirror, and then we've got the rotation stage. Actually, I've showed you all this before, so we can skip this. This was, it looks like schematically, we got the X-rays, the slits, the filters, this mirror. So now we have to, the beam that's coming off the mirror is coming down, well, because it hit at 1.5 milliradians. 2 theta off the mirror is 3 milliradians. So the beam right now is bouncing down at 3 milliradians, or about 1/6 of a degree. It's a pretty small angle, but it's big enough to matter for the tomography. So what we have to do is we tilt this lift table in the hutch by 3 milliradians. So now the rotation axis is not vertical, it's off vertical by 3 milliradians. This is the camera that we're using, and we're actually triggering that camera based upon the position of the motor. Because when we collect this data, we're not going to do a start-stop at each angle. We just continuously rotate the sample and take triggers out of the motion controller that tell us every time we've gone 0.1 degrees and trigger the camera to take the next picture. So we know that the camera is being triggered exactly every 0.1 degree. So this is a comparison of the pink beam and the mono beam. So this is the monochromatic beam, looking at a sample that's got glass beads and cesium chloride. This is the flat field. This is the image we see with no sample. You can see it's pretty uniform, but it's dropping off in intensity at the top and the bottom. That's because of the full width half max that I talked about for the synchrotron radiation. So it's most intense in the middle, and we're losing it top and bottom. This is with no mirror. And then we see some dark spots here. Those are actually little imperfections in the monochromator. Either like maybe a scratch, something like that. And then we've got some bright spots here. Those are some dust particles on the scintillator. And this is a data set that was collected for 1 second exposure time, 900 projections. So it took 900 seconds, 15 minutes. And you see we're measuring at just above the cesium edge, so the cesium chloride solution here is brighter than the glass beads. Now we do a pink beam experiment where the mirror is at 2.5 milliradians, and we've got a 2 millimeter aluminum absorber. So this is what I've already been through this with slightly different absorbers and angles, but this is red line is the incident spectrum that's hitting the sample. So you see, and this is now the cesium K edge is this green line. So you see most of the photons are below the cesium K edge. This is what the flat field looks like. You see there, it's got these strong horizontal stripes. Those are coming from the fact that our mirror is not perfectly flat. It cost $80,000 to get it like this flat. It's very flat, but it's not quite flat enough. So in places where the mirror is slightly concave, it's focusing the beam, and where it's slightly convex, it's defocusing the beam with a high spatial frequency. I don't know, maybe there's several hundred of these stripes along a millimeter mirror. So, they're, along a meter long mirror. So they're, centimeter period or, half centimeter period variations in the slope of the mirror. But because they're stable with time, they normalize out and they're not really a problem. There are also some dark areas here, which are imperfections in the mirror, and some bright spots that are dust particles. This is what the reconstructed image looks like for the pink beam, and you see the fluid, but you see it's less absorbing than the glass beads. That makes sense because most of the photons were below the cesium edge. There were a few that were above, but the bulk of them were below. And this, on the other hand, only took 13 seconds to collect instead of 15 minutes. We now lower the mirror angle to 1.6 milliradians, go up to a 4 millimeter aluminum absorber. The spectrum looks like this. Now, it looks like 2/3 of the photons are above the cesium edge and maybe 1/3 are below the cesium edge. Flat field looks similar. And now here's the reconstruction. Now you can see the fluid is more absorbing than the glass beads because most of the X-rays are above that cesium edge. Do the same thing, and you see in this case the cutoff energy of the mirror was at about 53 keV, 55 keV, something like that, because it's at 1.6 milliradians. And today we're at 1.5, so it looks similar to this with a slightly lower energy cutoff. So a cutoff, closer to 50 keV. This is going to 0.8 milliradians, and now you see the mirror is reflecting out beyond. We haven't hit the cutoff yet at 100 keV. This little glitch here on the red line, that's the platinum K edge. So we lose a little bit of efficiency or reflectivity at the platinum K edge, but it's still reflecting out beyond 100 keV. And interestingly, because we're at 0.8 milliradians on a meter-long mirror, if you compute the sine of that angle, which is that angle, it means we're only collecting 800 microns of beam in the vertical. But because that's as much as the mirror subtends at that small angle for a meter-long mirror. But because we've defocused it, we actually have a nicely uniform field of view, and this field of view here is 5 millimeters. So we've blown an 800 micron beam up to 5 millimeters. And this is what the reconstruction looks like. Again, not surprisingly, we've got a lot of photons. The fluid is more absorbing because essentially almost all the photons, or most of the photons now, are above the cesium edge. So this is just showing a comparison for a different sample. This is a cement that's some of the phases are doped with iodine. This is a monochromatic beam measurement. It took a half an hour. And this is a pink beam measurement that took 10 seconds. And, actually the pink beam measurement looks better. The cracks are better resolved. There aren't any serious artifacts. So, there are, and in this case, they didn't really need to do above and below iodine edge. The phases are bright enough just going above the iodine edge that pink beam works fine. This is an application of the pink beam where, one of the things you can do with the pink beam is you can do time-resolved measurements, right, for slowly changing things, things that don't change too much in 10 seconds. So this is an example of people that were, doing drainage and imbibition in sandstone. So they were flowing in an iodine doped water and then letting it drain and watching how the porosity changes, the pores drain. So they were collecting data sets every 60 seconds for 30 minutes while this column was drained. And, here's the time 0 and 30 minutes later. And if you look at this pore up here, you see that it's gotten significantly bigger because the liquid has drained out during this time period. Some of them don't appear to have changed. Let me just say a word about a few other tomography modalities. One is phase contrast. So phase contrast is what happens because X-rays are not simply absorbed as they go through the sample, but they can be refracted, just like visible light is. So if we imagine an incident X-ray on the boundary of air and a sample, it will be refracted. If this were visible light and this was a piece of glass, as you know, it would be bent towards the glass. This would be a lens that's focusing the X-rays down here. Visible light down here. X-rays are the opposite. They're actually refracted away from the solid and into the air because the refractive index is actually less than 1 for solids for X-rays, very slightly less than 1. So these angles are small. But what it does is it means that at this boundary, there are more X-rays than there should be here and fewer X-rays than there should be here. And that gives rise to edges that can enhance the contrast in materials. So here's an example where the user was trying to study rhyolite glass inclusions in quartz crystals. So, and these are measurements that were done with the sample at 30 millimeters, 100 millimeters, 150 millimeters, and 200 millimeters. So let's start at 200 millimeters, and you can, I think, the visibility isn't great here, but I think you can see that there's a more or less circular inclusion here that has a bright rim around it. And as we go to closer and closer distances, sample to scintillator, that rim becomes less and less visible. So at 30 millimeters, we're more or less just measuring the difference in the absorption of the rhyolite glass and the quartz. And their absorption is very similar. But their phase, which is the real part of the refractive index, is significantly different. The absorption is the imaginary part of the refractive index. And so we can see this inclusion, and she wanted to measure the shape. These are line profiles through those green lines. So you really don't see much at the boundary at 30 millimeters, but there's a really pronounced bright rim on the outside of the inclusion and a dark rim just inside the inclusion. So the X-rays here are conserved because the ones that should have been here, and they have been put over here instead. Phase contrast is something that you can do with a full field imaging. The next two tomography techniques I'm going to talk about can only be done with first generation pencil beam. So the first is diffraction tomography. So here we make a pencil beam, we put it through the sample, and we put an X-ray diffraction detector behind it, where we measure, an X-ray powder diffraction pattern. So we've measured the line integral of the diffraction along this line through the sample. And that can be reconstructed tomographically the same way that absorption can be. So we have to use first generation CT. So what you do is you select one powder peak out of that powder pattern, integrated powder pattern, for a particular phase, and then you basically reconstruct that tomographically. There are some constraints here. The grain size needs to be less than the voxel size because we're trying to get some powder statistics, and they shouldn't have a strong preferred orientation. This is an example of diffraction tomography done on a sample of the Murchison meteorite. So they were imaging 3 phases here: kronstatite, tauklinite, and forsterite. And they selected one diffraction peak from each of those 3 phases. And then this is the sinogram, which is distance across the sample for this slice as a function of angle for each of those diffraction peaks. And as the sample was rotated 108, actually I think this case 360 degrees. This is a reconstruction. They also measure the absorption. So this is a reconstruction of the absorption. This is a reconstruction that shows the absorption in a lighter color, and then a reconstruction of where those phases are. So you can see the forsterite is in green here, the tauklinite in blue, and the kronstatite in red. So you get a really nice, 2D section showing the distribution of those phases. Another pencil beam tomography that we do at GSECARS, but on the undulator beamline, is fluorescence tomography. So this is a focused undulator beam, focused to a micron or 2. And we're measuring here the line integral of the fluorescence with this fluorescence detector, again, as we scan and rotate the sample. So this is an example of fluorescence reconstructed for a virtual slice through a sample of an Arabidopsis seed, showing the distribution of iron, which is red, manganese, and zinc, and then it's composite colors. So if there's both, you'll get if there's both, you'll get purple. So this took about an hour and a half to collect a single slice. But one of the advantages of fluorescence tomography here is that it's a virtual slice. So first of all, you didn't destroy your sample, but also this slice is only 2 microns thick. And it might have been very difficult to section this material to be 2 microns thick and then do a conventional XY map of it. So you can make a slice that's very thick. We also have at BMD, and I'll show you, the ability to do tomography at high pressure. This is inside the 250-ton press, and we've got rotation stages here, top and bottom, that can operate while it's under a very high load. So we can put a sample, take it to high pressure, and do tomography on it. This is just showing it schematically. I'm getting a little late on time, so I'll go through this. But it's basically the same setup that we'd use for the absorption tomography we're going to do today, but we're inside the press. And this is an example application where they were trying to measure the volume of vitreous forsterite. If you want to measure the volume as a function of pressure of crystalline materials, it's pretty easy because you can do Bragg diffraction and use the lattice spacing. But for amorphous materials like glasses or melts, which is really the goal of this project, is you can't use diffraction. So one way to get volume as a function of pressure, to get the compressibility of these amorphous materials, is to simply measure the volume directly using tomography. This apparatus can also operate those 2 rotation motors synchronously, going the same direction to do tomography. It can also rotate them in the opposite direction to do shear. So you can do a shear experiment and then do tomography on the sheared product. One of the things that we're doing for the tomography at BMD is getting an apparatus that will let us do high pressure at shallow crustal conditions. So, kilobar or 2 with a triaxial deformation rig. That'll hopefully give us very good tomography images, better than we can get in the multi-anvil press under fluid, say critical CO2 or supercritical CO2, supercritical water conditions. Okay, I'm going to end up here with just showing you what some of the screens we use to control things on the beamline. So we're not going to be doing monochromatic experiments today, but if we were, this is the screen that's used to control the monochromator, stabilize it with feedback. These are the screens to control those 3 sets of water-cooled slits, the ones that are far away near the storage ring, the ones about halfway down the beamline, and the one just before the sample. This is the screen to control the mirror. So this controls the pitch. You see this is what it's at today. It's at 1.5 milliradians. The ellipticity and curvature here control the bending on the mirror. This is the screen that's used to control those absorbers in the beam, the filters. So today we're using a 1/4 millimeter of copper, but we also have available 2 millimeters of aluminum, 4 millimeters of aluminum, 0.5 millimeter of copper, 1 millimeter of copper, depending on how much of the low energy X-rays we want to get rid of. This is the control for the 5-axis optical table. This AX is the pitch of the table, which is set to an angle to match the pitch of the mirror here. This one's in degrees, this is in milliradians. And then these are the screens that are used to control the sample position of the tomography sample. We have a rotation, we have a vertical height, the 2 stages, tomo X and Y, that center the sample on the rotation axis, and these are the motors that control the camera. CCDY is the focus. I already showed you that screen. And then we've got the screen that actually collects the tomography data. This is done with a Python program that actually does everything like collecting the dark fields, flat fields, and projections, saving the data in HDF5 files. But all of these things are exposed as what's called EPICS process variables. If you don't know what those are, don't worry about it. But it basically means everything here can be scripted by other software. So you can write a Python program or an IDL program or a shell script that would automate this data collection and also change other parameters on the beamline and collect a scan. And you'll be seeing this as we do it in a few minutes. There's also a bunch of metadata that we can collect about the sample, about the optics and configuration of the experiment, and about the user. And that metadata is saved, both what you type here and a bunch of other metadata like the status of the storage ring and all of the beamline motor positions, sample temperature, and so on. And they're all saved both into a text file that you can look at easily, but also into the HDF5 data file. Okay, I think we're going to take a break here for, let's say, 8 minutes and start again at 1/2 the hour. Meanwhile, I'm going to go out to the beamline, and Tim Officer is going to be videoing me out there as I show you around the hutch, and then show you mount a sample and actually turn on the beam, and then I'll come back to my office and we'll hear about the samples, and then we'll actually make some measurements. Okay, see you. Okay, so now we are out at the beam line at 13 BMD, 100 feet from my office or so. And this area here is the control area where normally a user would be sitting to collect the data. And there's a computer on the left that's mostly used to control the screens for the beam line, and the computer on the right here used to control the screens for the tomography data collection. We have some monitors up above that are showing you cameras in the hutch. And after a data set is collected, users typically walk over this computer where it's a high-end workstation where they can do the data processing. Today, I'm not going to sit out here because, as I said, I'd have to wear a mask, but I have VNC sessions to both the computer on the right over there, the collection computer, and this data processing computer. I have those VNC sessions running on my office computer so that I can show you. It would be as if we're sitting out here at the beam line. So now I'm going to walk up to the experimental station. This is 13 BMD. And in this station, as I mentioned previously, there are 3 different experiments that go on that are done here one at a time, say roughly using 1/3 of the beam time each run. The first is the tomography experiment, which is here, and I'll describe that in more detail in a minute. There's positioned, basically using this same stage, we have a diamond anvil cell experiment here, which does what's called Brillouin scattering and X-ray diffraction. The Brillouin scattering optics are on a breadboard on top of this table up here. So there's a laser and a Fabry-Perot interferometer. And these optics back here are the optics that get moved into the beam path here. They're visible light optics that are used to deliver the laser beam to the diamond cell and then collect the scattered laser light back to the Fabry-Perot interferometer. The downstream end of the station here, we have the 250-ton press that I mentioned, and mounted in the press right now is the apparatus for doing high-pressure tomography. And to do that, this cell here, the Drickemer cell, would be used to put the sample inside that aluminum containing ring and squeeze with this 250-ton hydraulic ram down here, squeeze the plates together, compressing the sample to high pressure, and then rotating it to collect the tomography data with an imaging system back behind it. And then at the same time, or alternate with the image collecting, they can collect X-ray diffraction data to measure both phases and also see what pressure they're at, and that sort of thing. So now let me talk about the tomography in a little more detail. So these things right here is the final set of slits that I mentioned in my overview. These are in ultra-high vacuum, and they're water-cooled copper slits with tungsten carbide. And then this is the position of a beryllium window. Everything upstream of here is in ultra-high vacuum. There's a roughing vacuum section here, terminated by an aluminum window. If we're doing monochromatic beam, we replace this with a plastic Kapton window, and we have an ion chamber that mounts up here to measure the intensity of the monochromatic beam and do feedback. But we don't need that for the pink beam that we're using today, and in fact, the plastic would melt or burn up very quickly if we put it in the pink beam. So this is the optical table with the 5 degrees of freedom. And then this is the sample stage that I showed you. So the horizontal translation at the bottom to move the sample in and out of the beam. The vertical translation stage, 30 millimeters of travel. This is actually a slip ring system here, which allows these upper 2 translation stages to rotate continually without having cable wind up. So that, basically the motor controls signals pass through a slip ring that can rotate forever. That's a relatively new innovation, and it really helps to not have to worry about the cables tangling up as the sample rotates. Then these are those 2 translation stages to center the beam on the rotation axis. The sample, we can mount samples many different ways. Typically, often we mount them in a drill chuck like this. And we have a variety of sizes of chucks here because we can grab most samples in a chuck. But if you have an apparatus that specialty built, users often bring their own apparatus that mounts directly to this surface here, and happy to help with that kind of design. So then here's the scintillator that looks like a yellow greenish piece of glass. That's the single crystal of lutetium aluminum garnet, mirror, lens, camera. And then here is the camera stage to position the camera in X and Y, basically to center the camera on the rotation axis, and also to center it on the beam vertically and to focus. The entire camera system is mounted on a translation stage here, which can be used to change the distance between the scintillator and the sample. Right now, the distance that we're using is 40 millimeters, which gives an image that's mostly absorption contrast, not phase contrast. But we can drive this, and those phase contrast images of the melt inclusions in quartz that I showed earlier were done by increasing this distance, up to 200 millimeters. Got a couple of other cameras that are looking at the sample, so you can keep an eye on it from outside the hutch. And we've got the ability to do some in situ measurements here now. We do and we're getting the ability, as I mentioned, to be able to do high pressure experiments here as well. Okay, so I think we're ready to get a sample mounted. So I'm going to go grab one of the Chicxulub samples. So these are rock samples that you're going to hear about in a minute from the Chicxulub impact crater off the coast of Mexico, and they're basically, they were drill cores and then they're broken fragments, and I'm just going to mount a fragment on the drill chuck, Now these don't go in the drill chuck very well. So what I'm going to do is just put some plasticine or some clay-like stuff on top and push the sample into it a little bit, just so that it doesn't move. It's very important that the sample not move except for the pure rotation as you're collecting the tomography data. If it moves, you have artifact. That's one of the reasons we like to have these feed-throughs, so that there's no cable drag that's moving the sample when it shouldn't. The measurement is done with visible light hitting this that comes from the scintillator, so it's important that it be dark in the hutch. We're using very, very short exposure times right now because the scintillator is so bright, so that isn't as critical, but it's important to turn out the lights. So I'm going to turn out these lights, and then we'll turn out the overhead lights from outside the hutch. It's important that nobody be in an experiment station at a synchrotron when the beam is on, because it's not good for your health.
Okay, you're good. Stop for a second. Sorry.
There's a search procedure to make sure that nobody is in here, and I'm going to start that search now. So I'm going to walk up.
Searching station B.
You probably hear a voice.
Network issues, but I think it's all right.
Immediately.
Now I'm going to press this button. Probably be better. And now Tim and I are both going to leave. Now here I'm going to turn out the light, and I'm going to close the door, making sure nobody scoots into the hutch. And now it gives anybody who was caught in that station 30 seconds or so to go press an emergency stop button before the beam will actually come on. I'm actually going to turn the light on for a second. So you can see on the monitor on the left there, that's one of the cameras that was on the optical table. So you can now see the sample on top of the chuck, and you can also see that bright glow to the left of it. That's where the beam is hitting the scintillator. And similarly, the monitor on the right, that's just a camera at a slightly different angle. If I turn off the lights in the hutch, now everything is just illuminated by the scintillator. You can't really even see where exactly the beam is on that scintillator, but what I can do is because it's so bright, but if this slit, the horizontal slit right now, the final slit is 11.2 millimeters, because that's just slightly bigger than our field of view. I'm going to close it to 100 microns. So now, the scintillator is dim enough that you can actually see where the beam is located on the scintillator. So it's not right in the middle, it's a little below the center. All right, I'm going to go back to 11.2. And this monitor on the right is showing the image of the sample as viewed by the scintillator and the camera. So this is the image we're going to use to collect the tomography data. You can see those stripes probably from the mirror. But we'll be able to see this screen from my office. So I think we're going to head back there now. Okay, I am back in my office, and I'm going to put up the Okay, so now you should be able to see the screen, which is the computer, the data collection computer, the one on the right there at the Beamline. And it's got dual monitors, so I have to just slide back and forth here because I'm only sharing one monitor. So this is the image from the camera. The program that's displaying this is actually ImageJ with a plugin that knows how to display the images from our camera control system. So this is now looking at the sample that I just mounted on the chuck. The camera is actually, let me open the camera control screen. So the camera is actually got a size of 1920 by 1200 pixels. And with the lens that I'm using right now, it's actually exactly a 1-to-1 imaging lens. And the pixels on our sensor are 5.74 microns. And now the pixels on the sample, because it's a 1-to-1 lens, are also 5.74 microns. And that means our beam is 1920 times 5.74 wide, which is just over 11 millimeters. And vertically, if it were 1200, it would be over 6 millimeters. It turns out that even with the mirror maximum defocusing, I can't make a beam that's quite that tall. So I can't make a beam that is 1200 pixels tall. It's only 10, I clipped it to be 1020 pixels vertically, because that's all the beam I've got. And there was no sense collecting pixels with no beam in them. So it's about 5.8 millimeters tall and 11 millimeters wide. The first thing you do when you put a sample in is that you need to center it on the rotation axis. And what that means is what I really want to do here. This sample is a little bigger than the field of view, so which is violating my one of the things I told you about a requirement. But as I said, it's not a strict requirement if you don't want quantitative information, and it's not much bigger than the field of view. You can see we're seeing air on the right-hand side here, but we're not quite seeing air on the left. And this is at, let me go back to 0 degrees. So that was at 180 degrees. So what I'm doing now is clicking the rotation stage, and every time I click, it rotates 45 degrees. And so now I'm at 0 degrees. It looks like I could shift it to the left a little bit, minimize that air and get a little less of the sample out of the field of view on the right. That looks pretty good. Now I'll go to 90 degrees. And you can see that it looks like it needs to be shifted a bit quite a bit to the left. It's not centered. If you put things in a drill chuck, they naturally sort of get centered. But when you just stick it onto the plasticine, it's just as good as your eye is. Okay. And we're going to image this sample at multiple heights. So this right now, well, actually, let's go a little bit lower. So this is the vertical stage, and I just changed the step increment to 0.1 millimeters. So I'm going to lower it. So we're close to the top of the sample. There's the top of the sample. So we'll start at the top, which is at minus 2.4. And our vertical field of view here is 5.8 millimeters. And I think ultimately we're going to want to collect multiple heights on this sample. and we'll probably want to move it by a little less than the height. Oh, I just totally realized that I forgot that we're going to talk about the samples. Is Doug on?
Yeah, I'm here, Mark. Can you hear me?
Oh, yeah, sorry.
Yeah,
I
no problem.
forgot. That was the next thing we wanted to do. So I'm going to pause this and instead share Doug's slides and let him tell you about these samples, because he sat through this yesterday, so he may not want to sit through the whole rest of the thing here. So let me minimize this, and so this is Doug Schmitt from Purdue, who's the one whose samples these are, and he's going to tell us a bit about where they came from and why they're important.
Okay, so thanks, Mark. Yeah, this will be really quick. I just we've been involved with a lot of rock physics and field work related to impact structures, and so go ahead, Mark. Next, first slide. Oh, and so there's reasons we want to study these things are just basic knowledge about impacts and potential resources in certain areas like Sudbury there. But one thing that might be interesting, or if there's boots on the moon or on Mars in the next decades here, and we need to build structures, then it's going to be important to understand what we're building on. And a lot of those surfaces are heavily impacted, right, and highly damaged. So there's very few places on the Earth we can actually study that. And it turns out the Chicxulub impact, the one that killed the dinosaurs. Next slide, Mark. Sure. Is one of them, right? And so this is kind of just a figure of showing what you get on the left, right? They come in these impactors at, say, on the order of 20 kilometers per second, and so you got huge amounts of energy. And on the left kind of panel there, you see, you vaporize the impactor and you melt a large amount of material, right? That melts all over the place, and you can get big melt sheets even. And you get a lot of materials that are metamorphosed, damaged by the shock wave itself, put into high pressure phases and whatever. And then outside of that, you get a lot of just mechanical damage, as you might expect, right? And so lots of pores and things. And on the right there, you're just seeing, what basically the pressures that you see as you come out in that cartoon. And so what we're really interested in, we're involved. Go ahead, Mark. Next slide. Yeah, nice one of the dinosaurs. And so, of course, it's you can't call it Cretaceous Tertiary anymore, right? It used to be KT, but the geologists put their foot down, and we have to call it the Cretaceous Paleogene boundary, and that's a place in Alberta where it actually outcrops, and you can go put your finger on it. And so this is the big impact in Chicxulub that was drilled. Next slide, Mark, there. And this is a large seismic, couple hundred kilometers across. And what we're seeing there is basically you see the fill of the sediments that have come in since the impact and all the horizontal lines, but we also see there what are called peak rings. And what a peak ring is, those. And that's when you get impacts in complex craters, large craters become complex, and you get material moved quite far and from where it was originally sitting. And in peak rings, these are, instead of having a central mountain, you get kind of a ring of mountains that go around in very large structures like Chicxulub, right? That is on the order of 100, this peak ring is on the order of 100 kilometers in diameter. And so there was a lot of controversy about how those peak rings were formed and where they came from. Next one, there's just kind of a cutaway through where you get a central uplift. And this is seismic data that's come through. And so it was envisaged or thought that it came from deep, but then there were some, I don't know how much people are used to looking at seismic data, but the colors here represent seismic wave speeds. This was from surface seismic in the marine seismic and collected. And you come back, and this is from seismic tomography, actually, to get the velocities, the image in terms of velocities. But you also see there, you can see the K/PG. That's the actual reflection coming from the layer, from the surface that existed after the impact. And everything else on top of that is sediments. So what's nice about Chicxulub is that even though it's been around for 66 million years or so, it's relatively pristine, right? It hasn't been damaged that much by erosion. And so this Chix 03A is where the drilling took place to try and sample that and to get the peak rig rocks out to just try and see what's going on with them. Where did they actually come from? Because there was disputes about that. So go ahead, Mark. Right. And so this was a project we were involved with, just lots of pictures of the drill rig and getting onto the drill rig from the supply boats and the drill rig actually down there. It wasn't a big drill rig. The one corner is what some of the core looks like. That's a breccia, an impact breccia. And then just what it looks like on the sunset when you're, at the end of the day and you have nothing to do. So sitting out looking at the sunset. Next slide. And this is that on the left is what you saw in that size part of it, what you saw in the seismic before. And the central part is a geological interpretation of the core. And what we see is that there's a lot of what's felsic basement. And this felsic basement materials were probably laterally dispaced about 20 kilometers and vertically dispaced about 12 to 15 during the impact to make that peak ring. And what's really interesting from my perspective, because I study physical properties a lot, is that it's very low velocity. On the right, you see plots, different ways how the velocity is measured through the borehole seismic that we were involved with and through certain kinds of logs and some lab measurements at low pressure. And you can see the velocities there about 4 kilometers a second. And typical granite, undamaged normal granite, would be about 6 kilometers a second. So that's a huge deficit for those kinds of materials. And the porosity, actually in the density there we can see density should be about 2.6 or so grams per cc, and the density is about 2.3 or less. So it's very unusual materials, and so trying to understand it is important because it can actually give us some constraints on what the models are actually saying in terms of pressure and that. So next slide. And this was just our borehole seismic that we carried out there, and where you put the detector in the borehole and you make many measurements. And then next slide, coming up. And this is what that data looks like, and I doubt anybody in the crowd here knows what this is, but it's basically a lot of seismograms horizontally versus on the horizontal axis versus depth going down in the earth with the observations. And we can look at the velocities in there. In the panel in the left-hand corner there, you can see that pinkish zone or purplish zone is about 4236. That's in a kind of an average velocity. And that's all that granitic area, right? So again, we see that very high kind of damage zone in there. So next slide. And so here's plots of what the velocities look like in more depth. In the pink zone is basically that where that granitic material is. And again, about 4 and a little bit more, give or take, kilometers per second. And the different kinds of rocks up at the top, the sediments that came after the impact, the stuff called swavite that Mark measured a piece of yesterday, which was really neat. It's kind of the stuff that was at the top of the impact, and it was mixed with melt and real and breccia falling back, and so it's kind of and it was highly altered too. So it's an interesting material. And today he's got right now a piece of granitoid there, and that looks like granite, but if you actually can go and look at it very closely with your eye, right, it's quite friable and it looks damaged, right? So, okay, so I guess our next one, yeah, that's just an SEM there to show you how damaged some of that is. And so So we're really interested in, and so hopefully Mark can show us some nice fractures in this this granitoid material so that we can help to characterize it for basically the studies we're carrying out on the material right now. But I think that's about it. It's just we're looking for damage and how to characterize it. So
Great. Thanks very much. Are there questions for Doug? If not, I actually didn't ask if there were any questions for me earlier with my intro talk. So questions for either of us are fine.
everything was fully understood, I guess.
Everything was fully understood. All right. Okay, so I will go back.
Mark?
Okay.
Yeah.
Mark, I just have a quick question for you. So the intro talk that you gave this morning was really, really good, and I was just curious if you were planning on making the slides available in addition to the recording?
Sure, I'll be happy to do that.
Awesome. Thank you.
Yeah, the recording will definitely be available. I think it will. Charlie told me it takes like a couple days before Blue Jeans, it tells you it is, but maybe that's not true. I don't know. Okay, let me go to this one. Okay, so we centered the sample here up near the top, but I'd like to image this at multiple heights and do that just by translating it vertically. So I want to go see that when we raise the sample up and we get down near the bottom of it, that it's also reasonably well centered. And sometimes you have to compromise to center it, And because our field of view is 5.8 millimeters, I think we'll collect data sets every 5.5 millimeters, moving the sample vertically, because then we'll have 300 microns of overlap, and we can stitch the data sets together to build a gigantic data set of multiple heights. So I'm going to move this by 5.5 millimeters. So that would be the next height, and actually we don't even really on this one don't need to do that one because that where it's really dark at the bottom there, that's just the plasticine. So we could just image to here, and it's a little hard. It's bigger than the field of view and a little hard to tell how well centered it is, but it does appear that there's material on both sides. Maybe move it so the darker part is more in the middle, and then go back to 0. So it looks like we've got air on the right and not on the left. So let's just move it that way. It wasn't too bad. Okay. I'll say before we do like multiple heights, I'm just going to collect a single data set. And we do that with this screen over here, the tomography data collection screen. So on this screen, we set the start angle, which I have set to 0. The number of angles I want to collect, which is 1800, and the angle step size, which is 0.1. So it's going to stop at 179.9. You don't need to collect 180 because that's just the mirror image of 0. So you collect up through 180 minus delta. And there's a choice here. Do I return to the start position when the scan is complete? Usually with this setup, I do, but like with Yanbin's high pressure setup, those motors, because they're rotating under load, are very slow, and they can rotate forever. There's no reason to swing back to 0. You can just sort of collect your next data set from 180 to 360 and 360 to 540 and so on, and not waste the time rotating back. Then here, in this part of the screen, controls how we take the flat fields. So First, you choose when you take a flat field, what motor do you move? Do you move horizontally or vertically or both? So I can say X or Y or both. I've chosen X. And you have to set what is the sample in position. That's almost always 0. What's the sample out position? How far do I have to move it to get the sample out of the field of view? So I've set that to 20 millimeters. That's probably a little more than I need to move it. But if I say move sample out, now it's moved the sample out, and this is what the flat field looks like. Like I explained earlier, we have the mirror stripes. We have these little defects in the mirror that are dark here. Curiously, they are all symmetric. So that tells me something, but I'm not sure what. They come in pairs. Like this one in particular, it's obvious that there's a symmetry here, but I'm not sure why. And then these bright things are dust particles. They are the bane of my existence because they give rise to ring artifacts, as you'll see in the reconstruction. And they happen because this scintillator has a very high refractive index, containing a lot of lutetium. And so the light inside it has it does a lot of total internal reflection. And so in fact, if you can see it on the scintillator, a lot of the light leaks out the side because it's bouncing around inside the scintillator. This piece of dust now matches the refractive index of the scintillator better than air does. And so it lets some of that scattered light leak out. So the light in this dust particle is not originating here in the scintillator, it's leaking out here. And so that leads to intensities that are, meaningless, and thus to artifacts in the reconstruction. So I try to clean the scintillators, but on a field of view, particularly this big, it's really hard to get rid of all the dust. If I were imaging like 4 millimeter field of view, no problem. I could find a dust-free area here. But 11 millimeters is pretty big. Okay, so let's move the sample. So we've clearly 20 millimeters is enough to get the sample out of the field of view. So now I move it back in. Now we have to decide for the flat fields, when do we collect the flat fields? And you can collect them at the start of the experiment, before you measure the projections, or at the end, or both. I'm going to do both. And how many flat fields do you collect when you collect them? So I'm going to collect 10, but 10 at the beginning and 10 at the end, so altogether 20. And in the processing, those just all get averaged together. We can also collect dark fields. Dark fields would be the image with no beam. So we would have to close a shutter. I found that for this detector, basically there's no structure to the dark field, and it's more or less 64 counts in every pixel. And so I'm not going to collect any dark fields. I'm just going to tell it the dark value is 64. So when it processes, it's going to subtract that number from every pixel. And it's a pretty insignificant number compared to the tens of thousands that we have in the images. And then here you say, where do you want to collect your data? Did I say what sample this was, Doug? I actually need to go check that. That was a mistake. I meant to bring the bag from the sample in here. So you're going to have to give me 2 minutes to run and get that. So anyway, but this is where the sample, yeah.
Was that the one that I just sent you recently?
No, you know what it is,
Yeah.
I believe? I think it's the first one on your list.
Okay, I can dig that out if you want, so you don't have to.
Okay, it doesn't take long to do, I think.
Yeah.
And so you tell it where to collect the data, like a directory, and then also the name of the file in that directory. And if this directory doesn't exist, it'll create it. Here is where you set the exposure time. So I've set it for 6 milliseconds. You can see what happens if I change that to 8 milliseconds. Now it's the image over here is 65. It's saturated 65408. So we're too intense. We've exceeded the 16-bit data of this camera, so I need to go back to 6 milliseconds. And then there's a metadata here. So we could say, what is this sample? How far is it to the scintillator? What's the mirror conditions? You know, the username and their email. Stuff about the camera lens. So I've got this set correctly. It's 5.74 and the Nikon macro minimum focus, no tube. So let me go grab that sample bag just so we don't make a mistake. My mask.
While Mark is getting the sample, maybe we, if you have any questions, maybe I could try to answer.
Okay, it's sample EX07701.
Sounds good.
So because we might collect this more than once, I'm going to call this one A. We could do B, C, D, etc. And so now we've basically set our scan conditions. We've centered the sample and got our exposure time right and so on. So we're ready to go. So what I'm going to do here is hit start. Let me slide this over so we can both at this. So I'm going to say start scan. So what it's going to do is drive the rotation stage back to 0 if it wasn't already there, move the sample out, collect 10 flat fields, move the sample back in, and now it's rotating. And if you look down here, it's already a third of the way done, halfway done. It's done. So it just collected 1,800 projections and wrote them to that HDF5 file. Now it's doing the flat fields at the end, and now it is rotating the sample back to 0 because I told it to do that, and it's ready to go. So if we go look at this folder, you'll see that there are 2 files here. There's a config file. That's basically all of the parameters of this program. so that you can read this file back in and get back to the same conditions that this scan was collected with. So it's this is that file. It's basically got information about where we saved it, the scintillator, the user information, all of that, just in a simple text file. But it's written in what's called JSON format, so it can be easily parsed by computer software. And there's also this H5 file. So H5 is the extension for HDF5. HDF5 is a very well supported portable binary format. Hierarchical, you can put multiple data sets in a single file. So in fact, this file has the flat fields and the projections in it. It would also have the dark fields if we had collected any dark fields, and it has all that metadata, including a bunch of metadata that isn't in that text file, like where were all the motors on the sample stage, on the lift table, on the mirror, on the slits. So we know exactly what the configuration of the beamline was, what was the current in the ring current in the accelerator, all that kind of stuff is in that file. And now we could have gone over to the processing computer and reconstructed this. But I think what I want to do instead is to, before we do that, is actually to collect three heights on this sample. So we've got, multiple heights. And then I'll go change the sample and put another one in, one of the Swavite samples, but not the one we measured yesterday. And then we'll have something to compare these two. This is the granitoid, and then we'll do the Swavite. So to do the scan of multiple heights, we could do it manually, collect the data set like we just did, move it up, collect another one with a different name, move it up, collect another one. But I want to demonstrate that, this is all scriptable. So this is something called the EPIX scan record. So it can basically scan any EPIX PV. In this case, it's scanning M90, which is this vertical motor down here. So it's going to scan this vertical motor in a relative scan. I'm going to move from, let me see, I need to move it twice. Isn't that what we said? I think so. So if I go up 5.5 and up 5.5, that's as high as we really have data, because if I keep going, I'm in the clay. So yeah, so we want to scan it by a total of 11 millimeters. So we're going to do a total of 3 points, and we're going to scan it from starting at doing a relative scan. So we're going to scan starting here at minus 2.4 in 5.5 millimeter steps, ending at 11 relative. Step size of 5.5. So that's 3 points in the scan. And what it's going to do is move the motor and then basically press the start scan button and wait for the scan to get done, and then move the motor and press the start scan button again. But what I'm scanning here, it isn't limited to scanning a motor. I could be scanning the energy of the monochromator. I could be scanning the temperature of the sample. Anything that EPIX can change. So I think here now, oh, I want to call this B. And it's going to make, the first scan is going to be B underscore 001, B underscore 002, etc. I'm going to go double check that I've set that up correctly. So if I go to this screen and go look at the HDF5 plugin, yes, this thing means put the file number into the file name. So that's what it's going to do. All right, so now I'm ready to scan. So it moved the motor to the start, and now it's collecting a scan. So it shows you down here the elapsed time. So this whole data set is only taking 16 seconds. Now it's going to move it back in. You saw it moved it up. Now it's going to collect the flat fields for the second scan, second height, move it back in. And now the three data sets are done. The scan record moved the sample stage back to the start point of the scan, so the vertical position at the top of the sample, and everything's done. And if we now look at that directory, there's now a B data sets, and there are 6 files here. There's 001 config, 2 config, 3 config, and 3 HDF5 files. And you see each of these files is 7 million kilobytes, so 7 gigabytes. So we just collected 21 gigabytes of data. And we're doing that across the network. So this camera is a USB 3 interface. It can collect at about 350 megabytes a second, and our network is 10 gigabit, and so it can do about a gigabyte per second to our file server. So these were being saved on our file server. One of the things that I didn't show you, but might be interesting, is so this is the camera stage control, and I told you that this vertical, the Y stage here, adjusts the focus. So I'm gonna move this by 100 microns a few times. And I think you can see that the image got blurrier. Let me go 500 microns. Right, so now the image is quite blurry. Go back to where I was, and now go 500 microns the other way. So the first thing you've got to do, but only when you set up the optics, is to get the focus as good as I can get it. If I blow it up, better, worse. That's good. Okay, so we now did one sample, and what I'm going to do is I'm going to run out to the beamline and change this sample to the Swavite sample. So I'll be back in a few minutes. Again, if you've got questions, Yenbin maybe can answer them, or I'll be happy to answer questions when I get back as well.
I think you can either unmute yourself, ask a question, or type it in chat, or any way you'd like if you have any questions. This is a very quiet group today.
Okay, so I've put in this Swavite sample. It's EX20501. And I'm going to first, it might be a little too big. So I have a smaller piece if this is too big. So we're at 0 degrees. I need to center it with this one. So if I move the sample out, then the intensity in our flat field here is, it depends on where I am, like in this bright stripe that's almost 64,000, but down here it's about 44,000. When I move the sample in, it's about 6,000. So we're getting a little more absorption than I normally like, but you know, we can see how this works. And if it doesn't, we can put in a smaller sample. Or I can just image. I'll image another one because it's so quick to image. So this is going to be EX20501. This is A. And I'm currently, well, I can go a little lower. Go up closer to the top of the sample. Start it. This stage goes to minus 4.5, so I'm almost as low as the stage goes. Yeah, and here we've actually got air on both sides. I'll even go a little bit lower, where the sample's a little smaller. Okay. And now, if I do go to 5.5, yeah, again, it doesn't really make sense to collect data at this height because we're mostly seeing the plasticine. So just so we've got, we're going to move it once, twice, but not 3 times, just twice. So the same scan we did before is fine. Since it's a relative scan, it doesn't matter that we're starting at a different Z position. So I've set my directory and my file name. I'm now going to go, actually, I have not been updating this. I should do that, which is, but it's the same thing, EX20501. And so now if I do scan, so while this is going on, be a good time to ask questions. We got 41 people. Somebody's got to have a question.
Hey, Mark.
Yeah.
Yeah, can you hear me? Yeah, so this is
Yeah.
Dongzhou. So I was just wondering, so just now the progress sample, I mean the contrast is pretty good, but this one it seems very dark to me. So do you need
It's
to?
basically dark because it's so absorbing. I could probably stretch the contrast with image J. If I hit auto here, yeah. Now the flat fields, of course, are overexposed. But now you're seeing a little more. This is just stretching what's black and what's white in the display. But this sample is absorbing, 6,000 counts transmission compared to 40,000 counts flat field. So it's absorbing a factor of 6. So it's more like e to the minus 3 instead of e to the minus 2. And so we aren't going to have such great count statistics in the data. So I think after this, I'm going to go put a smaller chip on, and we'll collect the data on that, and then we'll switch to the reconstruction. Anybody? I got other questions?
Mark, there's a question in the chat. It says, how do you know if the scan is underexposed?
I'm not sure what exactly you mean by underexposed, but the exposure time has to be set on the flat field so that you don't saturate the flat field. And then it's a question of looking at the absorption to make sure that the sample is not too absorbing. But you can't change the exposure time to fix that. You have to change the beam energy or the sample size. But if you have a fixed size sample and you can't get the beam through it, it's too much absorption, then if you're using monochromatic beam, you go to higher energy. If you're using pink beam, you go to a smaller mirror angle and a thicker absorber, which is, again, moving you to higher energy. Okay, so that scan is complete, and we should have a folder for that. The 2051, again, with 6 things in it. And let me go put a smaller chip of this in, just because I'd like to make sure we get good data on this. And if this is too absorbing, if we do a smaller one, it'll work. Only takes a sec. Meanwhile, if everybody wants to take a 5-minute break, that's probably good. I'm going to get a glass of water. Okay, so I see a question here. Is there any principle to decide what energy used for the scan? So we're, it says voltage current. Now voltage current, that would apply to a laboratory machine. But again, you're basically adjusting the energy of the X-rays when you adjust the voltage, and you're adjusting the intensity when you adjust the current. So with the synchrotron, it's a little different. We adjust the energy with either the monochromator or the mirror angle and filters, and the current, we can't really control the intensity so much. We just control the exposure time. On a laboratory machine, you would adjust the current to try to not saturate your detector, but to get as much signal in a given amount of time as you can. Okay, so now I've got this smaller sample in. Oh, I didn't remember I'm moving it by a lot. This looks like when I moved it too much, did I bump something? I want to check the focus here. No, guess not. Looks fine. Okay, so I'm gonna move the sample so it's almost, we're just seeing the top of it. That's with the vertical adjust. It looks pretty well centered at 0 degrees. Go to 90, need to move it to the left a little bit. If I go by 5.5 millimeters, that looks fine. So now this will be B, the smaller one. There it is. We'll just say smaller piece. Okay, then it's this same scan again, because it's a relative scan. We're just going to do 3 heights. This is B. And all right, it's kind of boring watching that. So actually, I think I'm going to minimize this screen and go to a short talk on how we process the data.
So before that, Mark, I'm a Sunendra from University of Delaware.
Okay.
I have a quick question.
Sure.
So what about the other type of sample, like such as soil sample? What size of soil aggregates we can use for the analysis?
Basically, you know, the size is pretty flexible, you know, because we can change the magnification on the with our optics. We're limited by how high in energy we can go with a big sample, and we're limited by our field of view. You know, we really like to work on samples, I would say, that are, you know, preferably a centimeter or less in size. We're doing some bigger ones today. And we've done things up to, you know, almost 20 millimeters. Our scintillator is only 25 millimeters across. And as you go to thicker samples, you need higher energies, and eventually we can't get through it. And then on the small side, we have limits of resolution, which I see there's a question about that I'll talk about. But, you know, I'd say a lot of people who are doing soil aggregates with us, we work with a group from Michigan State. You know, they're looking at, say, they have columns that are about 8 millimeters on the inner diameter. And we can certainly do smaller than that. So our camera is 1920 pixels across, and we'll call it 2000. So our pixel size is going to be the field of view divided by 2000. So today we have an 11 millimeter field of view, so our pixel size is a little over 5.5 microns. If we had a 2 millimeter field of view, the pixel size would be about 1 micron. So does that answer your question?
Yes. So yeah.
Okay. So there is a question in the chat I see. Can we discuss what limits the tomography resolution? And exactly what I just said. It's the sample size divided by the number of pixels in the field of view. So ultimately, yes, we could go to a camera with smaller pixels and more pixels. And I actually have a camera. This one's 1920. I have a camera that's 2448. So it's somewhat bigger, you know, like 25% bigger horizontally, but it's 2048 vertically instead of 1200. So we'll be able to see a bigger vertical field of view. And ultimately, you know, the resolution is limited by the fact that we're using visible light optics. And we're limited by the diffraction limit of visible light and by the numerical aperture of our lens. So the same thing that limits the resolution of an optical microscope is limiting us. Plus we have some additional limits. But the numerical aperture of our 5x lens is such that it really probably doesn't have a micron resolution, because it's a long working distance lens, and we're limited to long working distance lenses because we want to have a mirror in there. We could probably get a lens that's a little bit better. We're also limited by the fact that we've got a finite depth to our scintillator. At the field of view we're using now, that doesn't matter. It's not limiting us, but if we had a small field of view and we were aiming for a micron pixel size, at high energy, the X-rays our scintillator is 250 microns thick. So we have a depth of focus effect that limits our resolution with the 5X lens. Now, if we went to very low energy, the X-rays all stop in the first 30 microns of the scintillator. They don't go through the full 250 microns. But these high energy X-rays that we're using today, they go through the full depth of the scintillator. One way to improve the resolution at high energy is to use a thinner scintillator. With the pink beam, that's completely feasible because the exposure times are so small. With a monochromatic beam, if we go to a thinner scintillator, our exposure times start to get to be too long. So I hope that answers that question. Matt asked point gray. Yes, this is a point gray Grasshopper 3 camera, but the new one that I'm using which is a USB 3. The new one I have it already, and it's in my office, is a point gray Oryx camera, which is a 10 gigabit camera. So it's about 3 times faster than the USB 3 camera. So it can do 160 frames a second with the bigger image size that I just mentioned, 2448 by 2048. And you said, how do you check if the sample is perpendicular to the beam? Very good question. So I do that initially. I put a metal pin in the chuck, and I move it so that first I center the pin so that it doesn't move when I rotate the sample. And then I move it with one of those upper stages so it's near the edge of the field of view. And now the tip of that pin, as I rotate, should stay in the same row of the camera at 0 degrees, 90 degrees, 180 degrees, and 270 degrees. 0 and 180 tells me, is the rotation axis parallel to the columns of the camera? If the camera is rotated slightly relative to the rotation axis, it'll move. It'll be higher on the left and lower on the right, or vice versa. If the rotation stage is not perpendicular to the beam, then at 90 and 270, when the pin is upstream and downstream, it will be in different rows of the CCD. So that's how I know that it's perpendicular to the beam. In practice, my rotation axis, if I level the table with a regular level, I know with the monochromatic beam, the beam is horizontal, the table is vertical, and my rotation stage is parallel to the table. So if I level the table, I know my rotation axis is vertical, I know the beam is horizontal, and I'm done. With the pink beam, I actually just calculate from the angle of the mirror what should be the angle of the table. I tilt the table to that angle, and I check it with the pin, but it's always right. I don't have to adjust it. Okay, if that's the end of the questions, then I think I'm going to go to this short talk. So for data tomography processing, you've seen what we do for data collection. We collect radiographs of the sample from 0 to 180 degrees. We collect one or more flat fields. We may or may not collect one or more dark fields, background images. So the first step of the processing is just to normalize the data. So for every pixel, we want to measure I over I0, which is the image minus the background divided by the flat field minus the background or the dark current. So now we have I over I0 for every pixel in every projection. So for this camera right now, we've got 1920 by 1200 pixels, or 1020 pixels, 1800 projections. So we've made 4.15 billion measurements of I over I0. The next thing we do is we convert each row of the detector. So we consider just one slice through the sample, which is one row of the detector. You convert that to a sinogram, and I'll show you what that is. But it's basically x versus theta. And you take the logarithm, because in absorption tomography, the thing that is the linear attenuation coefficient, we're measuring the line integral of an exponential, so we have to take the logarithm. Then you filter the sinogram with a high pass filter, and you reconstruct by back projecting from this XY theta space, that's how we measured, into XYZ space. And then you analyze your data. So I'm going to go through these steps a little bit. So here's an example of the raw projections. Here's an example of a flat field. This is a monochromatic flat field. like I showed you previously. And then this is simply this projection divided by that flat field. And you can see in the projection, it was getting dark at the top and bottom of the field of view. But once I normalize to this flat field, which also gets dark top and bottom, it looks uniform top and bottom. So that's the normalization step. It's pretty simple. So the next thing we've got, now consider one slice or one row of the detector as we rotate. So this is, the grayscale here is the intensity, and horizontal here is X, vertical is theta. And it's called a sinogram because if you think about any point in your sample as you rotate will describe a sine wave. If the point in your sample happens to be right on the rotation axis, it'll be a vertical line, which is just a sine wave with an amplitude of 0. So the first thing we do here is we take the logarithm. So now this is the thing on the right here is the logarithm of the image on the left. And then you put it through a high pass filter. So you basically get rid of the low frequencies and only preserve the high frequencies in the sinogram. And I'm going to show you why we do that. The next thing we do is we do what's called filtered back projection. So the filter was the previous step, and the back projection is this step. So a good way to think about this back projection is if I take the first row of this sinogram, which is the first angle, angle 0, and consider the intensity along this row to be a mask through which I shine some light. So where the mask is dark, the light going through is dim. Where the mask is light, a lot of light goes through. So this is just the projection of the intensities at 0 degrees. Now you take the next angle, but you project it from whatever that angle is, and you add up the intensities. It'll be at a slightly higher angle up here. And you keep doing this. So this is now the sum of the first 25 projections from 0 to 5 degrees, right? So the first 25 projections cover 0 to 5 degrees. So you now start to see places where, where what was dark at one angle is light at the other angle. So you're getting sort of, additions and subtractions that are adding up to an image. Now this is the first 45 degrees of data, simply summing up all those projections, projected from whatever angle it was taken at. Now this is when we get to 0, we've got 90 degrees worth of projections added up. And you're starting to see the sample. This is when you've done 135 degrees, and finally when you've done all 180 degrees. And we've got a reconstruction of a sample here. And you can see right away that if you had limited views, you couldn't do 180 degrees, you get an image, if you could only do 135 degrees because of some constraints of your sample apparatus. You can still get an image, but it's got these kinds of artifacts in it. But when you get to 180, you've gotten rid of the artifact. Okay, so this is going to show you why we have to use that high pass filter. This is what we'd get if we take that sinogram, we take the logarithm, but we don't put it through a high pass filter and we reconstruct it. This is a different data set. And you get something that kind of looks like your sample, but it's very blurry and the intensity is very non-uniform. It's basically the low frequency data is hurting you. This is what happens if I filter it with what's called a Shep-Logan filter. It's just a certain kind of numerical filter, but the length is only 10 pixels. So now, the sinogram looks much, we've gotten rid of a lot of the low frequencies. The reconstruction looks better. It's much sharper, but it still has an intensity dome. It's bright in the middle and dark on the edges. This is with a filter of a length 100. Now the image looks much better. This is with a filter that's almost the same size as the sample, a filter whose length is 1,000. And now we have a very nice looking reconstruction. So that's why you have to put it through a high pass. This is showing the effect of how many projections you collect. So this is the same data set, but I've thrown away all the projections except every 4 degrees. So when I only collect every 4 degrees, so I've only got 45 projections, I can see my sample, but there are lots of these streak sort of artifacts. When I go to 90 projections, now I'm collecting over 180 degrees, but I'm just coarsely sampling it every 2 degrees. It's getting better, but we still got quite a few streaks. 1 degree, streaks are there, but they're significantly fewer. Half a degree, better yet. And once we go to here, 1/4 of a degree, you really don't see the streaks anymore. We've collected, in this case, 720 projections. But this is on a smaller detector. I'm going to show now the effect of the rotation center. So if you think about the rotation axis is a virtual line in space coming up out of the center of the rotation stage. And that will project onto some specific column in the detector. And it's when you're reconstructing, it's really important that that position, that you know that position. And you ideally want it to sub-pixel accuracy. So this is a reconstruction of a sample where I think I've found the best rotation center. It's at pixel 343.5. And these bright objects, which are probably iron oxides in this sample, do not have significant streaks on them. That's at 343.5. This is what happens if I say that the rotation, if I use a rotation center of pixel 342. So I'm only off by 1.5 pixels from what I think is the best. Notice that these bright iron oxides are now highly streaked. They're sort of crescents with a facing to the left with a dark streak to the left and a bright streak to the right. If I use a rotation center of 345, which is 1.5 pixels the other direction, again, it's streaked, but the dark streak now goes to the right and the bright streak goes to the left. And so using this method, if you're lucky enough to have some bright objects in your field of view, you can manually figure out where the rotation center is pretty well. If you don't have any of those bright objects, it's more difficult. You can see, however, here that at the very top of my object, there's a streak going off to the left. And over here, there's a streak going off to the right. So you can sometimes use the edge of the object to figure out where it is. But if you don't have these bright things, it can be difficult to do it manually. But I've written software that can do this automatically. So it does it by varying where the rotation center is when it does the reconstruction. And for each reconstruction with a different rotation center, coming up with a figure of merit of the quality of the resulting image. And the figure of merit it's using is the entropy. And the entropy is basically just a measure of how sharp the histogram is. So you know what a histogram of an image is, how many pixels in different intensity bins. And if you measure how sharp that histogram is, the optimum rotation center is where the entropy is minimized or the histogram is sharpest. And what I do is I do that for 2 slices, one that's near the top of the sample and one near the bottom. They should be the same if the rotation axis is parallel to the columns of the CCD or the camera. But if it's not, then there's a mechanical alignment problem, and you can either fix it mechanically or you can rotate the images to make it so the rotation center is the same at the top and the bottom. And so this is a plot showing the entropy as a function of rotation center for a slice near the top and a slice near the bottom. And you can see they're off by like 1.5 pixels, something like that. So now we're going to get to what we're actually going to do today to reconstruct. So right now I'm sort of in midstream between converting from some old IDL software that I've been using for many, many years that does both the pre-processing and the reconstruction. I've recently switched from saving the data in a netcdf files into the HDF5 files you saw today. And I didn't change my IDL software to be able to pre-process these HDF5 files. I'm switching to what I want to use as the new software that's called Tomopy. And Tomopy can handle these HDF5 files. So right now I'm using Python and Tomopy to do the pre-processing step, which is the simple step I told you. Just read all the flat fields, read all the projections, subtract the dark current, divide by the flat field. And this Python program saves the resulting normalized data into a netcdf file. And then the netcdf file is read by my older IDL software that actually does the reconstruction. I would like to do the reconstruction in Tomopy, and Tomopy and my old software are nominally using the same C++ code called GridRec that's FFT based. I wrote it, I got it, or I didn't write it initially, but I made it so it's thread safe. It can be run on many cores. But I find that the reconstructions I get with my software and my version of GridRec are better than the ones in Tomopy. And I have not figured that out yet. I need to figure it out, fix Tomopy, and then I'll switch to Tomopy. So this is the program we're going to be using to do the reconstruction. Basically lets you reconstruct slices at the top and the bottom, figure out where the rotation center is, and then reconstruct the whole thing and do some simple visualization to look at the data. So that's what we're going to do now. So I'm going to close this and bring up a VNC session to the reconstruction computer, which seems to have gone to sleep. Should be able to wake it up with Control-Alt-Delete. Might have to go out to the Beamline to wake it up. This is annoying.
Hey, Mark, try clicking on the background.
I noticed it had gone to sleep yesterday, and I went out. I had to go do it at the Beamline. I'll be right back.
Are there more questions? I apologize. My chat stopped working a long time ago, so I missed a lot of chats. I'm sorry about that. 10-second scan. The length of the scan really depends on the exposure time per image. So we typically do somewhere between 700 and 900 projections. As long as each exposure time is short enough, you can actually take as many projections as you want. So in 10 seconds, it's not so difficult to get to 700 projections, or maybe a 900 or so. So the more transparent samples, shorter exposures, you can get more, of course. So the way the exposures, the projections are timed is a number of the total rotation angle range from 0 to 179.99 something, and the exposure time. You divided that computer calculates, software calculates how many exposures you can get within the exposure time limit, and that basically gives you the maximum number of projections You can choose to do fewer than that, but not more than that.
Also, Yamben, I want to ask you, I'm not sure if I heard Dr. Mark right, but I think he said that the beam would melt the plastic parts if it hits it. Is that true?
I'm sorry, we say it again. The beam would to melt the plastic.
I think I heard Dr. Mark say that the pink beam, if it hits a plastic object, it would melt it.
It could, if the sample is very absorbing and the beam is very, if you don't do proper filtering, you could actually project a lot of thermal energy on your sample, and then you could melt it. So typically what we do is we do some calculations to begin and see how much beam is transmitted and what kind of energy is best for doing the contrast. So we don't just put a sample in with a beam and then zap on it.
So then what is the best way to hold the sample?
Oh, holding the sample is not too bad. It's not like you're actually putting a lot of force on the sample. It's the thermal energy. It's not there's not like a strong wind or things like that.
Now, my question is, like, if you have a soil aggregates or you have a fine particle soils, then how do you put that in you need a container, right?
Yeah, you can. If you have loose samples, then you need a container. So
yes.
The container is better to be more transparent than your sample.
Yeah. So what kind of container is good for the holding samples?
I think any container would work. Depends on the absorption of your sample. But you could have a plastic ring. You could have some Kapton tape around the sample. It varies from sample to sample.
Okay.
So if your grains are very, very light and very transparent, then it's better to have some even lighter material around it.
Okay.
Because otherwise you kind of degrade the contrast.
Mm-hmm.
If your container is more absorbing, then in most of the X-rays, the contrast is it's overwhelmed the sample. That's not ideal. So you do a lot of trial and error.
Okay.
I see another question. Is it possible to micro exafs hotspots? It's possible to do the micro exafs, but the absorption becomes a more important issue. Oh, Mark is back. Maybe Mark can answer that better.
What's the question?
So the question is, if you find some hotspots in the sample, can you do micro exafs on that spot? It depends on the absorption edge of the exact.
Yeah, that's right. I mean, typically, we've been looking at samples where it depends what element it is. So if you wanted to do iodine and cesium, yes, but those are typically not very interesting elements to do exafs on. So the problem is we can't get a beam through the sample at the iron absorption edge or the manganese absorption edge or zinc on typical sample sizes. Also, you'd be measuring, you can't put the beam just on that one point because the beam's going through all the rest of the minerals or whatever in that slice, right? You would really need to make like a 2D section to do that. And there was a question, how many projections for 10? Did you answer that?
Yeah.
Okay. Sorry, that computer would not wake up, so I had to reboot it. Don't know why. So now you're going to see me sort of start from scratch here, which is actually not much. So the first thing I need to do is create two I need 2 Windows Explorer windows. The data that we've been saving is on our file server, which here is the T drive, Tomo user 2020. You see, I've been doing it for a while. Data goes back to 1998. And run 3, Schmitt, pink beam. And then we're going to copy the data across the network to this folder over here on the local drive, which is a fast solid state drive. The data set that we just collected, let's see, today we did EX0771. Okay, so let's copy that one over. And then I need to open a Python window. And I'm using Anaconda Python. And I need to do CD or d:/cd Tomo, data, Tomo user, Schmitt, pink. Okay, so let's do the first slice in the stack, which is B001. So I say Python C, Python, got to remember the name of the program. This is the problem with command line. So preprocess 13bm.py, and we want to process B001. So that's going to read that B001 HDF5 file, find the flat fields. Sorry, I have to say conda activate TomoPy. So that's reading that HDF5 file and finding all the flat fields, averaging them together, dividing all the projections by those flat fields. So now it's in the normalizing step, dividing. And then it's going to write that out as a netcdf file. So now I need to start IDL, which is where we do the reconstruction. This machine so it has 48 cores, 128 gigs of memory, and solid state disks in RAID 0 configuration, so they're like parallel. And so it's a high performance workstation. You don't really need this many cores for the reconstruction. It doesn't use this many. But you do need a lot of memory if you're going to look at this tomography data. Okay, so now I say Tomo display, and that brings up this GUI that I've written. And now this is done. In fact, we can be pre-processing the second data set while I reconstruct the first one. So now I do read volume file, which is a netcdf file, and I need to go to D data Tomo user net pink ex, and there's that first data set that's been already normalized. So this has been normalized. Okay, so if we just display a slice, so this data set is now 1920, that's the horizontal, by 1020 vertical by 1800 projections. If I display a slice, it's called here, in the Z direction, that's going to be a projection. So that's the normalized data for the projection at 90 degrees. It's a little bigger than the screen, so let me zoom it a half. So you see most of the stripes from the mirror have been normalized out. There's still some faint stripes there, which means that the image must have been moving. You can see some faint stripes, so it must have been moving the mirror stripes a little bit between the flat fields, but that's pretty good. So that's what the image looks like. If I say make a movie, that would just play the normalized projections as if we were rotating the sample. So let's go reconstruct a slice, and it shows you two slices here, one that's 10% down from the top and one that's 10% up from the bottom. And it guesses that the rotation axis is in the middle of the field of view, 1920/2, 960. So I'm going to tell it to reconstruct a slice, assuming the rotation axis is at 960. And you can see that it's got some streaks going off to the left. And so that doesn't look like it's quite the right center. Let me guess that it's 970, because I know that's where it was yesterday. Let me see if that's any better. That does look quite a bit better. You see how these streaks are now gone. In fact, this bright iron oxide or whatever it is here now doesn't appear to have any streaks. So that's a good sign. So that means the rotation axis is not in the middle of this field of view. It's 10 pixels off, which is about 55 microns off. And now I could reconstruct the slice down at the bottom. It was also using 960. You can see that looks really bad. We got lots of streaks because there's lots of oxides in this. Let me try 970. And again, that looks pretty good. I can set, this is auto scaling. So, it takes the brightest pixel and makes that white and the darkest pixel and makes that black. I can set that I want to manually scale it. Let's say from -200 be black and 2500 or maybe 2000 be white. Now when I reconstruct, we'll get a little better contrast on this. So, we can see there's a more absorbing mineral, this bright one, surrounded by a less absorbing. There are some significant holes in it here. These are voids. And then the bright iron oxides and lots of cracks. But I don't know that 970 was exactly the best rotation center. So I can optimize the rotation center. There's a couple of ways of doing that, but the one I talked about just previously was the entropy method. And I'm going to tell it to optimize over a range of 6 pixels, so plus or minus 3 pixels from my guess of 970 in quarter pixel steps. And when I press optimize center, that's now going to reconstruct both slices 24 times, quarter pixel steps over 6 pixels. and it's going to plot the entropy and show me where the minimum is. So that's the bottom slice and the top slice, and this is the plot of the entropy, and you can see that the entropy is at a minimum for both slices at exactly the same place. Well, at least on this graph. Numerically, it said one of them was at 969.5 and one was at 969.75. So they were off by 1/4 of a pixel out of like 800 pixels. So it's very good. If it was not mechanically well aligned, which it is, if that was off by more than a pixel, I would then press this button, which says correct rotation tilt. It figures out from where these two centers are in the slices, that's an angle. And it knows, okay, I now need to rotate every image by that angle. And once you do that, then the rotation centers should be perfectly the same. You've basically brought the rotation axis into the same column of the camera over the full height. But we don't need to do that because it's so good. So I'm going to just say reconstruct all. Even if these are different now, it is going to use, at this slice, it's going to use this center. At this slice, it's going to use this center. And it's going to interpolate and extrapolate out. So that can make the images better even without rotating them, to have the rotation center be correct, be the best it can be for that slice. And it's always linear. So now it's reconstructing all 1020 slices. And it tells you here, and it does it in chunks, and it actually reads the input file, reconstructs, and writes the output file all at the same time. So the reconstruction is going on in the background, the file I/O is going on in the foreground, and it says reconstruction is complete. And if you look at the IDL window here, it says it spent 10 seconds reading the input file, 12 seconds writing the output file, and it only spent and other time converting the input to float and the output to integer. It only, out of the 45 seconds here, it actually only spent 11 seconds waiting for the reconstruction. All the rest of it was the file I/O, because the reconstructed file has now already been written to disk. Okay, so now it's reconstructed. We can read it in. So that's this recon.volume file, which is also a netcdf file, but it's now the reconstructed data, not just the normalized data. This file you can read into ImageJ, you can read into lots of other processing programs. So now if I display a slice in the Z direction, that's going to be one of the actual slices in the sample. Actually, the one in the middle is the one it chooses. So that's now the slice in the middle of the sample. If I say make movie, it's now going to fly through all the slices in the sample, one slice at a time. So we're basically going through the sample 5.8 microns at a time. Now you see all those rings, those are called ring artifacts, and they're annoying, and they come from those defects in the mirror and the dust particles. So I'm going to find a place here where there is, let me read in, oh, no, I'm going to say display slice, and I'm going to look for a slice where those ring artifacts are pretty bad. This one, in this slice, they don't happen to be bad. Let me just see if I can find one where they're. Well, there's one that's pretty bad. That's way on the outside, not too bad. Okay, well there's some there. You see this ring and this ring, and that's slice 687. So what I'm going to do is now read back in that unreconstructed data, just the normalized data. And I'm going to reconstruct it again, this time trying to suppress those ring artifacts. So I'm going to tell it, instead of slice 102, I'm going to use 687, where we think there's a ring artifact. There they are. And this program allows you to do ring artifact suppression. It does that by averaging all the rows in the sinogram, which is, all the projections for this slice. And when you average all those rows in the sinogram, all the angles, that should have very little high frequency content in it. These ring artifacts come from certain pixels in the detector having an anomalous response compared to their neighbors. If you average the sinogram and then you smooth it and you look for deviations from that, you'll see pixels that have either too low of a response, and they'd be dark here, or too high of a response. And you can correct that. Basically, figure out by what percent are those pixels anomalous and scale them by that value. You choose a width by which you want to do that smoothing of the sinogram. And the default here was 9 pixels. But if I change that to 100 pixels and then reconstruct that slice again, now you see that those ring artifacts are greatly reduced. You don't really see them. So what I'm going to do is reconstruct the whole thing. So let's go back to slice 100 and tell it to optimize the center again. On the correct slices, one's near the top and bottom. Now it's got the centers. Now let's reconstruct all. But now with 100 pixel ring artifact removal. Usually with the monochromatic data, you don't need to make a big ring width like that. The anomalies are they're mostly small dust particles. I think they're not the bigger things we have on the mirror. Not quite sure why. But with the pink beam, typically there's worse ring artifacts, and you got to suppress them more here. Okay, so it's now reconstructed it again. So let's read that new recon volume file in. We'll fly through it as a movie and see if it looks like it improved, that we've got fewer ring artifacts, which I'm sure we will. There's still a few. And we'd have to look to see, are those... This is actually a problem. These bright oxides look like a ring, and so it's actually introducing some rings here. So we might want to play around with it to come up with something that gets rid of the real rings without introducing more rings. Okay, that was looking at the data, horizontally. We can also slice the data vertically. Y here is the vertical slice parallel to the beam. So, that's the slice through the middle in the vertical direction. Again, we can say make movie. Actually, let me abort. And these things that move left, right, like this dark thing here, That's one of those ring artifacts. But the bright things that don't move horizontally as you fly through it, those are real. Those are iron oxides. And, the cracks are showing up really well here, as are all the different minerals. I should point out that when we look at this in the Z direction, go back to zoom a half, there's only really valid data here in the inscribed circle in this square. That's where we've actually measured the data. So this stuff that's outside that inscribed circle, and there isn't so much of it here. If we go further down, is there more? Yeah. So this stuff that's outside the inscribed circle has incomplete data. And so it gets poorer quality when you're not inside that circle. Okay, so now we've reconstructed the first data set and we've pre-processed the second one. I'll pre-process the third one while we're waiting here. And now we'll reconstruct the second height in the sample. So we just read in the 002 volume. And again, we're going to guess that the rotation axis is at no, we do that in this optimize, 970, optimize it. The rotation axis shouldn't have moved much, but if our vertical stage isn't completely vertical, if it shifts things, actually, I'm going to turn this back down to something like 30 because it looks like it's making those bright oxides into fake rings. If my rotation axis isn't perfect, it could be moving. I'm sorry, if my vertical translation stage isn't perfect, it could be moving the rotation axis. So we got 969.0 and 969.25 as the optimized values. That looks great. So all we got to do is say reconstruct all, and it'll reconstruct this one. And so now let's go and copy over the this data set. Which was the swavite. And so now we've this one is reconstructing. I want to go here to that data set, the swavite with Python, change the directory, and it's already finished copying data sets 1 and 2. It's probably still copying 3. So we're going to go to Python here, and we'll load in data set 1, pre-process it. So this is now reconstructed the second height. While this is doing the pre-process on the swavite, we could reconstruct the third height on the granitoid. So I see I got a couple of questions. What's a single stack size in gigabytes? Okay, so that we can just look at the volume file here. at the directory. So the one we were just working in is here. So the raw data sets that you saw were about 7 gigabytes, 6.988, and the recon volume files are about the same size. They're 7.3 gigabytes. And the IDL code for the reconstruction, and it needs, I would say you want to have, maybe 3 or 4 times this size. So I wouldn't try, I would say at least 32 gigabytes, because you're going to want to do, one of the things that we're going to want to do is to create something that's as an array that's as big as 3 of these files, and then fill it in with the data from the first data set, the second data set, and the third data set, and then write that back out as a big file that contains the entire stack. And it's fastest and most convenient to be able to do all of that in memory. So that might actually entail having enough memory to have 4 times 7 gigabytes, which would be 32 gigabytes would be enough. But actually, it's amazing how inexpensive RAM has gotten. So, get 64 gigabytes. Yeah. And then could you go over a little more detail about the processing? Chris, what kind of processing steps? You can unmute yourself. Okay, so it's read this one. Let's optimize this third data set, 970, optimize center. This all gets to be pretty routine. And to some extent, as long as your samples are all pretty similar like this. Okay, so by the third height, it looks like we're starting to get some, it's bigger than the field of view, and it's showing up with a different intensity because it's not normalizing to air. But we can still get a reasonable reconstruction. And we optimize the center okay, so let's do reconstruct all on that third one. And then as soon as that's done, I'll go over to the swavite and reconstruct that. So yes, the Matt's question, I took 3 heights. I don't know if I'm going to have time to do it today, but yes, it's basically very simple in IDL. All you do is you create an array that's as big as, all 3 of those stacks put together. You read the first data set and stick it into the first part of that array. You read the second data set and stick it into the second part of that array, taking into account the overlap. So you don't stick it in at the very end of the first data set, but 300, we had, you figure out how many pixels of overlap you have. Because we know how many pixels, we know how many millimeters we moved it, and we know how many microns per pixel, so we can figure out how much overlap there is. And you copy the second data set into the big data, combined data set at the correct slice. And then you've got a 3D data set, you just save that back as another recon volume file. That's got all 3 data sets in it. So how would this change for a diamond cell when the sample dimensions are much smaller? Basically, you'd have to have a much higher field, a higher magnification, and to get smaller pixels. And we also have the problem with a diamond cell that typically you can't get 180 degrees of unobstructed view. So you either live with the artifacts you get by whatever field of view you have, or you use a different. This is not an iterative reconstruction technique that I just did here. You saw it was one pass through the data. There are iterative reconstruction techniques where you read the data, you reconstruct it, you calculate what that sinogram would have looked like from the reconstructed data. You compare it with the actual sinogram, and then you use some figure of merit to try to improve the sinogram that you're working with to so that the observed sinogram better matches the predicted sinogram from the reconstruction. And those iterative techniques tend to be very slow. So, it might take overnight to do a good reconstruction using an iterative algorithm. But in the end, hopefully you end up with a significantly better reconstruction. Okay, so we've now reconstructed that third data set. Let's go look at the other sample. So we're going to do read volume file, not in this folder, but in this folder. So I've pre-processed the first data set. I could be pre-processing here the second one. Okay, so now we've read in that one. We think the rotation axis is still going to be 970. Let's optimize the center. Okay, so it looks like actually the rotation center has changed a little bit. It looks like it's at 972. I'm pretty sure I found a clear minimum, but I can simply do this again and it'll center that optimization on the best rotation center it found on the previous iteration. So now it's going to be centered at 972. And again, the mechanical alignment looks really good. These are a little dark, so I think what I'm going to do is instead of going to 2000 here, I'll go to 1500. So anything 1500 or higher will be white. So now we see a little better contrast. Clearly, this is a pretty different looking rock. We've got whatever these are. I've seen these in some of the other ones. It's a very irregularly shaped mineral with a bright rim. And it would be, interesting to look at this in a thin section to figure out what that is. You've got these lath-shaped crystals, which are probably plagioclase, and then lots of these bright things, which I assume are iron oxides. But it's possible that they're sulfides. But I would guess in this rock, it's more likely that they're oxides. Although it seems like there's an awful lot of them. That's not the number of oxides you see in a typical igneous rock. So again, now we can do reconstruct all on this sample. And we could be pre-processing the third one here. This is actually kind of nice that I can be pre-processing in one window while I'm reconstructing in the other window. Previously in IDL, it was sequential because here you pre-processed here and you reconstructed here. Although what people would do would open two IDL windows so they could be working on two samples or two heights at the same time. And my intention is not to leave Python as a command line thing, but to build a GUI around the TomoPy as well. So I wish that the TomoPy reconstructions had been as good as these, and then I wouldn't have to, I could have been moving the TomoPy already. Okay, so that reconstruction is complete. Let's read in that recon volume file. So if we display a slice, that's now the slice in the Z direction. We can display a slice in Y, vertical, and we can display a slice in X. So X is the other vertical direction, the one that's perpendicular to the beam. Y is the one that's parallel to the beam. X is perpendicular. And yeah, again, these funny looking minerals with bright rims around them. And this is that Swavite sample, which was quite thick and quite absorbing. And I'm seeing something here that looks like it could be something that's called beam hardening. We're using a polychromatic beam, so there's not actually a single well-defined linear attenuation coefficient, which is what we're reconstructing here. And you see how it's kind of bright up in the upper right here, and it gets darker down below. I think that's because our beam down below, we're really absorbing all of the low energy photons. And whereas up here, some of the low energy photons make it through the sample. And so it's not giving the same absolute linear attenuation coefficient where the sample is thinner and where it's thicker. But for seeing what Doug wants to see, which are basically looking for the voids and cracks in here, it's probably okay. If we were imaging those samples, I can find a smaller shard of this, and I did, where I don't have that problem. And you can see here that it's going outside the field of view everywhere, right? Because the sample's too big for the field of view that we were using. In fact, we could, in this directory, there was the B was the smaller shard. So let's try B001. So it'd be interesting to compare that. And that doesn't take too long. But meanwhile, we're sort of finishing up here. It's getting to be 5 o'clock. Are there more questions? Comments? Don't be afraid to unmute yourself.
We have one here from Jamal. It's the
Okay.
fastest total time. Capture
Two
two
consecutive scans. Probably about, the saving is happening at the same time that it's collecting, and it's keeping up. So there's no time to wait for the capture, really, for the saving. And you could turn off the flat fields, right? You could save some flat fields at the start of the scan, early on, and then during a time resolve scan, not bother to collect anymore, because the flat fields are pretty stable with time. So then it's really just the time to do that rotation step. And that's, I think today we were seeing it was 16 seconds, and that was to saturate the detector. Although it actually probably was controlled more by, well, I guess my answer would be maybe 10 seconds with what we've got today. The fastest fluorescence tomography scan, that depends a lot on the concentration of the element that you're looking for. In the Arabidopsis seed fluorescence scan that I showed, zinc and iron and nickel, I think it was nickel, the third element, those are trace elements, right, in a seed. They're not present at major element concentrations. So, I think that one said it took an hour and a half. But that's because, you had to count for a while in order to see those trace elements. If you were looking for something that's more of a major element, but irregularly distributed, you could do it faster. But still, let's say you need, it depends on the resolution of the thing you want. But, let's say you wanted a 512 by 512 image. That takes roughly 512, well, it takes 512 translations and maybe 512 rotations. So that's 256,000. If you counted for a hundredth of a second, and you can get a reasonable spectrum for a major element in a hundredth of a second, then it would be, 250,000 points divided by 100. So that would be 2,500 seconds. That's about 40 minutes. So you could probably do a good fluorescence scan in somewhere between 20 and 40 minutes if the concentration's high enough.
Also, Dr. Mark, I want to ask you, currently, what's the upgrade schedule for the Beamline? Will it be available in next summer?
You're talking about the bigger stage? Is that the what
I'm
kind of upgrade are you talking about?
I just wonder if, like, for 2022, the second for
Right.
2022, will the beam be open, and also for the summer of 2021?
Yes, the APS upgrade. Okay, so there's two different things. There's me upgrading my tomography stage. Hopefully that's going to happen in 2021-1, next run. The APS upgrade is currently scheduled to begin in like June of 2022, the machine completely down for a year. There's been no announcement that schedule has slipped due to COVID or due to any other factors, although the possibility has been raised that it would slip for 6 months. And so that the beam would actually go down at the end of 2022, and come up, end of 2023, early 2024. But there's been no official decision about that. But for the next at least year and a half, the beam will be running, and maybe even a little more than 2 years, the beam will be running before it shuts down. Okay, so I just did the pre-process and read in the Swavite, but the one that was a smaller sample. So we can see what that looks like compared to the one that was very thick. And you can see here that the top slice that I selected, that it selected 10% down from the top, there's actually not much sample there, because if we look at the projection here in Z, the sample is petering out. We got air on top. So what I'm gonna do here is to increase this slice to maybe slice 200, where there'll be a little more sample before I do the optimization. And sometimes you have to do that because there's no sample 10% down from the top or 10% up from the bottom. So sometimes you have to figure out which slice is it that you can optimize, top and bottom. So we don't have a lot of sample, but we've got significantly more now. And so now this sample is staying, at least, top and bottom, this part of the sample is staying completely in the field of view. That looks pretty darn good. So now let's reconstruct the whole thing. So yeah, we're reconstructing 10-20 slices in, what was it, like 45 seconds or something? Yeah, 45 seconds. Like I said, when I started doing this in 1987, it took 1 hour to reconstruct one slice, and the slices were nowhere near this big. So yeah, computers and detectors have come a long way, because there were no such thing as 2D detectors in 1987. There weren't CCDs, there weren't CMOS, there were no, even video tubes. You could kind of buy a TV camera and look at a phosphor, but the signal to noise was terrible. So now let's read that V recon volume. Okay, so there was a question about how many shifts people apply for. So, I mean, you could do, as you saw, particularly when you're running with pink beam, you can do a lot of samples in a day. you can collect terabytes of data in a day. So we often have people that only have 1 day of beam time. In COVID, when I'm the one changing 10 hours, but when the users are here, it's 24 hours. So in 24 hours, you can collect a lot of data. So a lot of people only get 3 shifts. If you're trying to do some in situ measurement where there's an apparatus you need to set up and get optimized and sort of that, then a day is often too short. So we give people 2 days or even 3 days of beam time for those kinds of experiments. And there are even some monochromatic beam experiments that are slow. We have a user who is, they're soil scientists and they're interested in looking at organic matter in soil, and X-rays are not so good for that. Seeing carbon. So what they do is they stain the organic matter with osmium and then image above and below the osmium K edge. But the osmium K edge is at 74 keV, I think, which is very high energy, and the beam is weak. So it takes quite a long time to make those measurements, and then we give them more beam time. Okay, so go ahead.
Oh, I'm just saying thank you. I hear that. It's
Okay.
most of my sample is actually in diamond average cell, but you just said it probably has a little bit of limitation on scanning like the quenched sample and stuff. So
Yeah, I mean, there is another beamline at the APS that does what's called nanotomography,
okay.
where they use, we aren't using any X-ray magnification on this beamline. All of our magnification is optical. So we're limited by the diffraction limit of visible light at the very best. So if you want to do better than that, better than, let's say a 0.5 micron or a 3/4 of a micron resolution, you have to blow up the X-ray beam first and then image that with visible light. And they have a beamline for doing that at sector 32 at the APS. And they can get down to, under 100 nanometer resolution. But it's not at very high energy, 10 keV maybe. So it would be difficult to get through the diamond, but it's a good technique for imaging samples after they've been recovered from the diamond cell, or potentially through a diamond cell with a beryllium gasket. I don't know if that's been done. I think it's been tried. I don't know how successful it's been. Yeah.
Yeah, thank you so much, because I have some paleontologists, a friend that want to scan some, let's say, brachiopods. Then I would say this beamline is like perfect. It's like from nano brachiopods to like bigger size and see how the muscles is formed inside the beam.
Right.
Perfect.
Yeah, I mean, like I said, we can scan small fossils. We can't scan big fossils.
No,
And we can't scan fossils where the mineral has been replaced by pyrite, because it's too absorbing.
Too absorbed.
Yeah, but the silicate or carbonate fossils of sizes up to a centimeter, 15 millimeters. Yeah, we can scan those.
That's perfect. Thank you so much.
You're welcome. So now let's look at this sample. Okay, so there's the vertical slice of the swavite smaller chip. And now if we go to unzoomed and make a movie of that. Our network actually seems a little slow today because this shouldn't be so jerky. If we were at the computer out there, it would not be jerky. It's something to do with the VNC connection here. But you can see how well this images those cracks, which is what it is that I think Doug's really interested in. We got a few ring artifacts, but I'll try to clean the scintillator better. Okay, I think that's probably good for the demo, but I'm happy to stick around and answer any questions people have.
Okay, I have a question.
Yeah.
About like temperature sensitive samples, is there kind of like a low end melting temperature that you suggest to not use? So let me give you an example. So like something embedded in like a gel that might melt.
You mean melt from heat?
Yes.
Okay, I would say, I mean, when we use the monochromatic beam, there is zero heat. When we use the pink beam, I have not actually measured it, but I don't think the sample heats up significantly. What's more potentially of a problem is radiation damage. That with the pink beam in particular, you're putting a lot of photons on the sample. And I mean, the radiation damage that's clearly visible that we see is like I was making a whole bunch of measurements in a plexiglass load frame earlier this week, and the plexiglass turned brown. Often, and certain kinds of glass will turn brown. Pure silica does not, but microscope glass, when you put the beam on it, it'll turn brown. And like when we've done white beam studies, or pink beam studies, I should say, of fluids, of water in the cell, and I showed that time lapse, they had to do some optimization not to hydrolyze the water. So the water breaking down, into oxygen and hydrogen and forming bubbles. It turned out by getting rid of most of the low energy photons by putting in a copper filter, and then only opening the shutter when they were actually making the measurement, so open the shutter, make the measurement, close the shutter to minimize the dose to the sample. They were then able to run for many hours without forming bubbles.
Okay,
but
great.
If you have an organic gel, I can't guarantee what's going to happen to that in the pink beam. Any more questions?
Hi, Mark. I have just a general question about different applications for pink beam versus monochromatic beam. So I understand that in some cases you can use different kinds of beams to highlight different absorption for different phase minerals, but could you elaborate a little bit, just basics of what sort of application for different types of beams?
Yeah, I mean, the monochromatic beam is essential if you're trying to image like above and below the absorption edge of a particular element. And I showed examples where we were going above and below the absorption edge of cesium and iodine. And those are the edges that people often use for fluid studies. But for minerals, a user who's come to the Beamline quite a bit is a guy named Gil Gualda at Vanderbilt University. He studies pumice. And one of the things he's used the tomography for is to try to locate and visualize the trace mineral phases in the rhyolite. And those phases include zircons. And in fact, finding zircons in the rock is really important because zircons, of course, are used for age dating. They've got the uranium lead series age dating. And he was also looking for other trace phases like sphene. So he imaged above and below the zirconium edge, and that would show him exactly where all the zircons were in the pumice, or above and below the cerium edge, showed him where the sphenes were because the sphenes contained significant quantities of cerium. And, so for trace phases that contain high atomic number elements, the monochromatic beam is good. The monochromatic beam in general, I would say, particularly for if you're trying to go to very high resolution, it is, at least right now, until I get a thinner scintillator and try that, it's giving better resolution. When you're trying to push down to a micron or so. But it's slower. I should also say that, we have a high resolution monochromator, which is great for going above and below the absorption edges. But it has a very small bandwidth, as I said, so it has low flux. There is another beamline at the APS, and I probably should have mentioned this. It's 2BM, 2 bending magnet. And they don't have a high resolution monochromator, but they do have what's called a multi-layer monochromator. So that's kind of in between pink beam and monochromatic beam. So, the pink beam has a bandwidth of, let's say 100%. It's 20 keV wide at 20 keV, or 50%. It's 10 keV wide at 20 keV. Whereas the high resolution monochromator has a bandwidth of 10 to the minus 4, or 0.01%. The multi-layer monochromator has a bandwidth of about 1%. So it's in between the high res mono and the multi-layer and the pink beam. And so they sort of specialize in pushing to higher resolution. They can't make an 11 millimeter field of view like we did today. They only have, they have a 2x objective and a 5x objective and a 10x objective. And that's all you can use. And so you can't make a big beam, but if you're trying to get to a micron or under a micron, that might be a better beam line to work at. So for the diamond anvil cell that Kanani was asking about, they've done diamond anvil cell work. Not a lot, but they have done some. But if your diamond anvil cell sample is 100 microns in diameter, let's say, and they've got even, micron pixels, you're only going to have 100 pixels in your image. Even half micron, which is probably pushing it, even at sector 2, you'd have 200 pixels. So you're going to get pretty limited resolution on a diamond cell sample without using projection, X-ray projection, like the nanoprobe beamline sector 32. More questions?
I think Sector 2 also have a drone plate setup before, but they closed that setup a couple of years ago. So 32 is the only option. You can use the drone plate setup to study sample like diameter 20 micron, and you can get the spatial resolution down to 20 nanometer to 30 nanometer. Regarding the energy, like Mark mentioned, they don't have really high energy, but they can push up to 19 kilowatt if you don't really care 30 nanometer resolution. If you only get 50 nanometer resolution, you still can get energy.
Okay, well, that's good to know. Yeah, I didn't know those numbers. Thanks.
Right. Yeah, so we play that in last 10 years at Sector 2, Sector 32, so we know some detail there.
Right. Right, and there is another tomography beamline as well at the APS that's open for general users. That's 7BM, and they do white beam, and I think they do pink beam. I'm not positive if they have a mirror there. But they're mostly focusing on very fast time resolution. So they're studying like fuel sprays and things like engine injectors, where they want to see what happens in orders of milliseconds or microseconds even. They can't do tomography at those timescales, but they can do radiography. And I should say we can also do that, and we do that. I was doing it this week. So I had a user who was squeezing single particles of sand between two pistons, and wanted to do tomography to understand the contact angle, the contacts between the grains and the pistons. But then we were doing radiography to watch what happened at the instant that they fractured. And were they fracturing gradually and opening up some cracks, on the time scales of tens of milliseconds, or were they fracturing essentially within a single frame? So we don't have to be rotating the sample. We can just be collecting radiographs as fast as we can, up to 160 frames a second.
Mark, so if we were to do in situ deformation, in situ experiment, and with rotation and flow tomography, so I guess the shortest time scale for deformation, I guess deformation would be like tens of seconds. That
yes, if you want to see it in 3 dimensions. If you're trying to do something more quickly where you just want to watch the initiation of a crack, it's possible you could do that with radiography, and then the time scale could be much faster, milliseconds. But to get the full 3-dimensional information, well, the rotation stage I have right now, it only does 30 degrees a second. That's as fast as I can go because it's a stepper motor and a gear. And that means that would be 6 seconds to go 180 degrees. The new stage that I got, the air bearing stage, can go significantly faster than that. I have to look at the specs, but I'm pretty sure it can go more than 1 revolution a second. So you can go under, 1 second. And we could acquire the data, but in 1 second, we would only be able to collect 160 frames, right? So it would be pretty limited angles. So are you interested in situ deformation?
Yes. So, so I guess if say, faulting, fracturing happens within a few seconds, at the moment, we can't really capture. But if the faulting happens over a minute or something, we could.
Yes. I'd say that's true. And we may be able to push that in the future. Right. I mean, at Sector 1, they are doing very fast. Sector 2, I should say. They rotate the sample and they wait for something to happen, and then they trigger the acquisition. So they're not constantly collecting the data, but they're constantly rotating. And what they're actually doing, they've developed, just in the last month, they've developed a streaming data flow. So they're streaming the data to a server where they can reconstruct not the full data set, but you can actually do reconstructions just of 3 slices, 1 horizontal and 2 vertical. And you can do that, at 100 frames a sec, at 100 hertz. And so you can be watching your sample in 3 dimensions with just a limited number of slices. And then when you see something happen, start to stream the whole data. And there are ways, let's say you're rotating at 5 revolutions a second. You're not going to be able to capture that many frames for each revolution, but you can actually combine information in the rotation domain and the time domain. So, you can go, let's say you collect one good data set slowly, and now you collect sparse data sets quickly. You can reconstruct what's changing better than you can reconstruct the whole thing. So there are ways to push the time resolution for dynamic phenomenon, even though we're not doing full sampling at that full rate.
Thank you so much, Mark.
I'm not an expert in that.
Kind of along those lines, Mark, with dealing with increasing speed of rotation, you end up necessarily, like you said, because of the frame rate limitations of the camera, you end up decreasing what your angular resolution is then.
Right.
Do you have kind of like a rule of thumb as to what your minimum angular resolution is on this type of measurement before it starts to become a little bit too shady?
Well, I think I showed in the what do we get if we only sample every 4 degrees, in the reconstructions,
Right.
even at 4 degrees, which was how many? What's 180 over 4? I mean, it was 40. A very limited number of projections. The data. Let me just pull that up. That was the. Yeah. So, I'm not sharing my. I was still sharing my screen. I didn't know that. Okay.
Yeah.
So with 45 projections, which we could do that at quarter second time. If we can do 160 frames a second, so we could do 45 projections approximately in a quarter of a second. So we could get an image that looked like that in a quarter of a second, and in a half a second we could get, or a little more than a half a second, we could get an image that looks like the one on the right.
Mhm. Okay, I know some of the preliminary stuff that they've done at XPD. They've been doing 1 degree steps, and I was trying to convince them to go a little bit tighter than 1 degree, just to make sure that we were getting something solid. So this is a good comparison to see.
Yeah. There's a 1 degree step. To my, if I do. If I build a slideshow and do view zoom. How come I can't go more than 100%?
You have to select the object first.
Oh, select that?
Yeah.
Okay. Yeah.
Oh, yeah.
So that was 1 degree.
Mm-hmm.
Whereas if I that was 720.
Right.
Quarter or half degree. Quarter degree.
Yeah, there's definitely a visible difference there.
Oh yeah, I mean, yeah, you're way undersampling at 1 degree. I mean, depending on how many pixels in your camera, but sometimes.
I'm using the same one that you were talking about, 2448 by 2048. I've got that version of the USB 3 version of the Grasshopper 3.
Okay. Yeah.
Yeah, the biggest issue is we're running with the monochromatic beam and a YAG instead of a LUAG, so we have like 1 second per image as the exposure time. So they were trying to balance out what the exposure time is versus what information they're going to be able to get from the rotation.
Yeah, that's exactly the trade-off that you have with the monochromatic beam. And you're using like what kind of a field of view?
My resolution that I have set right now is 1 micron per pixel. So
I see. So it's a pretty small field of view. It's only 2.5 millimeters.
Yeah.
Yeah. And then I think at our beamline with our monochromatic beam, and we don't have a wiggler, right? We got a bending magnet. There, the exposure time would be, I mean, to saturate, it would probably be 10 seconds. Typically I live with only using 10% or 20% of the full well, and it's still a couple seconds.
Mm-hmm.
So, with monochromatic beam, we might, and particularly at those kind of high resolutions, we might collect for a half an hour.
Right. All right, cool. Thank you very much.
But with the wiggler, you should be like 100 times faster.
Yeah, I mean it so I think what I'm trying to focus on is getting a better scintillator, because when we're dealing with a 67 keV beam, having a YAG there is not the ideal scintillator
Yeah,
for
no, no,
what
no. You
we're
should get a
for,
LUAG. Yeah,
yeah, we're actually looking at, I think it's a lead tungstate one. It's one similar. But it's
yeah.
only 5 microns thick, so we're
I
still
see.
going to be dealing with a trade-off. But we're looking into one that they're using. I think they're using it at HXN and one or two of the other beam lines down the way at NSLS2. So there's
Okay,
a
I'll be
guy.
interested to know what you find with that because
Yeah,
I need
absolutely.
to get some thinner, better scintillators too. I mean,
Yeah.
I've got some 100 micron LUAGs, but I don't have any like real thin scintillators. I got some other scintillators from Sector 32 to test that were higher Z, but they weren't well enough polished. So
Mhm.
they just didn't do very well.
Yeah, what Kaz was suggesting was to get I think I'm pretty sure it's a lead tungstate or a cadmium tungstate. I think those are the two different ones that
Yeah.
he was talking about, and he was recommending 5 micron thickness for the scintillator on some sort of substrate. So I was like, well, if it was polished quartz, we could actually have the mirror built onto it, um, and be able to have a single assembly that way. So that's something that we're looking at and discussing there. But I'll definitely keep you posted on what we find out.
Yeah, I mean, one of the things, I mean, because you can buy, from this, this company Krytur, they're in the Czech Republic.
Yeah.
They sell that's where I've been getting my scintillators,
Hmm.
and they'll sell thin scintillators that are mounted to a substrate. But my question is, what glue are they using,
Right.
and how radiation damage, and they may work fine in the mono beam, but in the pink beam, I'm worried about that. And
Yeah.
so I've thought about asking if they can, basically you need a substrate just so you can handle it. But could they do it so that it's like glued to the edge of the substrate is a donut with a hole in the middle, and the business part of the scintillator is actually unbacked,
Right.
but the
Yeah.
edges are
Yeah.
held. Yeah.
Hmm. Hopefully when Kaz gets back, I'm going to have a meeting with him in a few weeks, so I'll figure out where things are at, and I'll let you know if anything new comes up.
Okay, sounds good. So which hutch does this happen in at XPD?
This is mine. So we're actually using the camera and the imaging system that I have set up for the multi-anvil, and we started doing some tomography tests using a strain rig that I don't know if you knew Nick Simos. He's a nuclear engineer guy, but he had developed a strain rig, and we were testing that in XPD, doing some preliminary experiments, and we basically set it up right in front of the press and did rotation, but instead of vertically, the rotation was horizontal in this particular rig. But yeah, we used our optics and our camera and everything to see, kind of test its feasibility.
All right, now are you guys still using like the Questar telescope,
Yeah.
Questar optics? Yeah, okay.
Yeah. So that's actually the same Questar lens, just 40 years newer, is the one that they're using for the tomography setup that they built at the front end of the XPD D hutch. So the nuclear sciences that's developed that Tomo station there, they actually did a search through lenses, and they found that the one that we were already using was the best one. So they went with that one, and it's just, like I said, it's 40 years newer, and so it has motorized controls, so you don't have to run in and out of the hutch every time to check focusing and things like that.
I see. Yeah, we should talk offline about that.
Okay.
Yeah, I mean, does that have variable magnification?
Yes. Yeah, field of view and magnification. So I can back it off so that I can get a full 1/4 inch almost in field of view. But the way we have it set right now is exactly 1 micron equals 1 pixel. And since the samples that we're dealing with are a maximum of 2 millimeters, in vertical height before squeezing, it's perfect because it gives us, for the experiments that we want to do, we want to have as much of a change as possible. So we keep the sample as as close to the edges of the image as possible, and then any deformation we do from there comes in.
Right. Oh, great.
But again, because we don't have the motorized controls, we have to go in and out to make any changes to it. So it's less than ideal, but
I see. Any more questions? All right. If not, I think we'll say everybody have a great weekend and hope you learned something.